Hello, I'm Roy Ogus, and today is May 17th, 2019. I'm here again at the Computer History Museum in Mountain View, California with Robert Garner, and we're about to start the second session of Robert's oral history discussion. Thanks again, Robert, for your participation.
Oh, my pleasure.
In the discussion at the end of the last session, you had come to the end of your stint at Sun Microsystems. The year was 1998, and you were contemplating a move from the company. Before we move on to the next phase of your story, I thought I would ask you whether you have any other comments about Sun Microsystems that you'd want to bring up before we move on to your next chapter of your story.
Oh, thank you, Roy. Well, again, thank you very much for doing my oral history. It's
My
just
pleasure.
wonderful. I liked the part one part, so part two will hopefully be just as fun. And I will try not to talk as fast and try not to interrupt you. So one story, one little tiny story I forgot to tell at Sun before I move on. It was kind of emblematic of the way things happened there. Is when we were actually just before the Genie project started, there was really a move to try to produce a really inexpensive computing device, a diskless PC-like device, and there was a strong feeling we could get it down to $1,000 for a selling price, or even less perhaps. And so Bill and I and several people were in a room, and we were looking at the bill of materials for how expensive or inexpensive we could make a diskless PC. So it'd get all its information over the network from other servers, kind of anticipating a lot of what we do today. And I came up with this bill of materials, and it was much under $1,000, so it looked like maybe you could sell something for $1,000. And right in the middle of all this, Bill Joy gets a call on his cell phone, and he starts going, "Hey, we just figured out we can get a bill of materials done for a portable system for much less than $1,000." And Bill put down his phone. I said, "Bill, who was that?" And it was the head of Oracle. Larry Ellison. I said, "Bill, you just..." And then the very next morning, I'm driving to work, and I turn on KQED, and there's Larry Ellison talking about how he thought we could do a network computer for under $1,000. That was the fastest transfer I ever heard from idea, no implementation, idea to PR on the radio. And then he gave a talk, that very Friday, and he compared the network computer to the versatility of a pencil or something.
So what was the year that Oracle acquired Sun?
Oh, that was much later.
Much later. So
Yeah.
this was nothing to do with that.
This is in 1997 or 1996.
Okay, that was much later.
Yeah. And I mean, Larry Ellison had a personal relationship of some sort with Scott McNealy, and Larry had helped bring, or Scott worked with Larry to bring some of his database software to Sun during the early days, because it was kind of embarrassing in the very earliest part of Sun. I'm not sure I told this story before, but Sun was had a manufacturing facility in Milpitas, and our volumes were increasing, and the rate at which we could ship products was being hindered by something which was rather surprising. A friend of mine helped set up the manufacturing facility there, and there was a backup in the system, and there were actually boxes of Suns ready to be shipped in the parking lot. They couldn't be shipped because the rate at which an entry to the part number for that device could be removed from the computer was slower than the build rate. So there were actually components accumulating in the parking lot. And apparently, the software we're using was running on an IBM mainframe somewhere in Southern California. And when my friend looked at the algorithm, it was a linear search algorithm through the parts list to delete, or to add, to say one of these components had shipped. And that was slower than the time it took the manufacturing facility to build them. So Sun was in dire need. They may have been running on an Amdahl machine now that I think about it, an IBM compatible Amdahl machine somewhere in Southern California. So this was very early at Sun. This is in the, probably in the 1988 time frame, somewhere in there. So yeah, Larry Ellison and that whole thing came later. But that's a good segue to why I thought it seemed like the time had come. That Sun was being eaten from below by, like I said before, the Intel Pentium line had actually slightly surpassed, same clock rate, 300 megahertz UltraSpark 2 compared to a Pentium 2, slightly surpassed us in performance. And people were getting more capable of building shared multiprocessor memory systems and more capable systems. So I just felt the writing was on the wall, that we were going to get eaten from below by Intel devices. And the Genie project, it was a lot of fanfare, but it was clear that it was a long way from being a practical product. Sun was starting to purchase on a regular basis smaller startups. And it was kind of disillusioning. They would just purchase them and then eat them up. And politics was starting to get more intense at Sun. It had become kind of a big company. So I was really longing for the opportunity again to be at a small company where you have much more control of what your future is going to be. Harking back to what Eric Schmidt had told me when I joined Sun, that, whatever happens here, whatever you do, it will become a product. You don't have time to cancel projects and start whole big projects. I mean, Sun had gotten to the size where we were starting, either through acquisition or on our own, large projects which would be canceled. It struck me as, all large companies, tech companies, this happens to, is pretty inefficient. So the startup model, I think, is much more efficient because you focus on a particular idea or product, you fund it sufficiently, you bring it to market, and you're tested immediately. You're not necessarily just doing a project to keep people on the payroll, or to keep their managers happy. There's less infighting at a startup. At a large company like Sun was at the time, if you have project A and project B, and they each think the other one is not worth doing, you get all this infighting. So I wanted to try to also move away from that and go back to a startup. One of the popular magazines at the time, trade magazines at the time, was Upside magazine, and there I read of a startup doing a network storage system using fiber channel. And and it sounded pretty exciting. They had funding. They were about a year and a half old. They had an initial product that they were selling. This is before the .com era has come. Things are heating up, though, in the Valley. So my first thought was, well, fiber channel, okay. It all sounds good, but is IBM doing a fiber channel switch? A switch was the main product that Brocade was doing. Companies had fiber channel. Let me back up a second. There's a broken sentence. Fiber channel initially started as a connection between high-performance disks. You could string the disks together on one serial cable, and somebody would get on the bus and they could talk, and someone else could get on the bus, but it was serial. So if you had 127 disks, all 127 disks would be on one Christmas tree serial loop. So the innovation that Brocade had done is, let's give a port to each disk, and let's make it cheap enough, have enough ports so that we can, perhaps some of those ports would be connected to serial loops. Maybe you would have 8 serial loops. So, give some switch technology to improve your latency and response time. And which is great, but if the big behemoth IBM was going to do a switch, the days would be numbered for Brocade, or any other company for that matter. So this reminded me a little bit about the risk opportunity. Remember back in the early part of our risk work at Sun, we were worried whether IBM would do the right thing and come out with a great 801 derivative in the workstation market, and they didn't. So here we are again. I'm going, well, okay, here's a startup. Is IBM going to tromp over everybody? And so I poked around, asked people questions, and it appeared as if there was this huge battle inside IBM for, on the one side there was Fiber Channel, on the other side was their internal architecture.
So did you actually talk to people at IBM as well?
Well, I probably can't say that. I certainly talked around.
Right, so you got inside information.
I tried to get inside information of what IBM was doing, and it seemed to be not totally secret. So, because there were a lot of discussions were happening at public standards meetings. So I said, okay, let's go for it. And in some ways, so the firm I decided to join was Brocade Communications in the summer of in '98, after 14 years at Sun. And I came on board as the director of hardware engineering, reporting to Paul Bonderson, who was the first employee at Brocade. And Paul had been the director of the I/O group at Sun Microsystems. Probably not the most well-known group at Sun, because Sun was focused on the CPU and its Sun OS Solaris software. But Paul had done an outstanding job leading the I/O group at Sun. And in fact, that's where the ideas for Fiber Channel came from. Sun had parallel SCSI ports on its workstation, where you have many lines in parallel just to connect to one disk drive. So clearly you needed to make that transition. Ethernet made it first to a serial line. You needed to make the transition from all these parallel bits to a serial line to the disks. And so the Fiber Channel work had started before Brocade was founded. Kumar was one of the architects, and the other place where the serial bus transition happened was to memory DIMMs. And that was so all the main interfaces in computers were high throughput was important. We're transitioning to serial lines, high-speed serial lines. It was, of course, not as high. We may not see it as high today, but it was 1 megabit per second and 3 megabit per second at that point.
So you knew Paul Bonderson from before. Did you know anyone else at Brocade?
Well, what's interesting, I didn't know Paul that well, because he was kind of over in different buildings across the bay. But he knew about me, and he certainly could get advice from some of the Sun people.
The reason I asked it was I was wondering how much of your decision to go to Brocade was based on people you knew there.
It was not. It was not based on that.
Not at all.
No,
Okay.
It was more based on I thought they had a great idea, and IBM wasn't doing it, and it was really going to fly. And that turned out to be true. It turned out that Brocade entirely dominated the Fiber Channel switch market. They became essentially the sole supplier to ISV supplier to the entire high-end computing market. So it just exploded. They did have they had talented architects, just like we had talented architects at Sun. I can count on one hand the number of really talented architects who really understand how to do architecture, not let their egos get too much in the way, and work with designer teams. So Dave Banks on the hardware side and Craig Martin, extremely talented architects, and a really talented architect on the software side. When I first arrived at Brocade, there was a design review for a tape out of their very high-end ASIC, the next key switch chip. And I sat through the design review, and I asked a question. I said, well, okay, over here we have some asynchronous signals coming in. Where is the synchronizer? And it was like, oops. They had forgotten that they needed a synchronizer. And, Dave, there's more issues you have to deal with in a chip of that complexity with, 500,000 gates. So Paul liked to joke that I already paid for my salary the first year because the cost of spinning an ASIC is extremely high.
Well, that's a good thing for your...
Yeah.
He wasn't your immediate manager.
He was. Yeah,
he
was.
was.
Paul Bonderson was my immediate manager.
So that's a good thing for him to feel.
Yeah, he was VP of engineering, and I was director of hardware engineering. At that time, the hardware team, it was truly a scrappy startup. The hardware team was only 4 people. And over time, I grew that to about, 7 engineers. And over time, I grew that to about 30. So maybe there were 4 people on the ASIC and 3 people on the board. It was a pretty tiny team, incredible team.
How big was the company as a whole at that point?
Oh, when I joined, it was pretty small. I was like employee 130 something, so it was pretty small.
A few hundred people.
Yeah, a couple hundred people. And again, they were doing everything. They were even doing their own manufacturing of the switch. Obviously, they and everyone else moved away from that pretty quickly. But so I had responsibility for all the hardware aspects: the engineering design team, verification, the development, compliance test, and then field support for the 1 and 2 gigabit. I'm sorry, not 1 and 3. And the products were called the Fiber Channel Silkworm 2000 and 3000 family by the time I was there.
Yeah, you told me if customers had hardware problems, they'd come to you, and
yes.
You were the support group as well, yeah.
Yeah, you had to do everything at a startup. I guess the Bloom chip was 10 million transistors, an 8-port switch, and so that was what was fully defined and working by the time I joined. And the silicon did work the first time after it came back. So yeah, I had to directly interface with customers and manufacturing problems. When we started manufacturing the Silkworm 2000, they were getting random test fields and failures in manufacturing. And it took a while to figure out, but it would depend on whether certain other items were plugged in or not, power supplies. And there's this bus called the I2C bus, which is used a lot in systems, and it's a serial bus that links together chips for which you can run serial JTAG, as it's also called, through to read out the state of registers and stuff in chips. And it's a poorly designed bus. It was designed a long time ago. It's just a single wire, essentially, and it's multi-branched and not terminated well. So what we learned, or what I discovered, is there were errant reflections on that bus. So depending on what was plugged in, and what was worse is that the problem got worse when the characteristic impedance of the printed circuit board changed. So the problem came upon us when all of a sudden we were getting printed circuit boards from another supplier. So I had to, and here's a switch, which is at the heart of your storage subsystem. It has to work. It can't not deliver bits from the disks to the processors, right? So we had to communicate with customers and tell them that, we found the problem, we understand when it comes up, the boards you have, don't have this low characteristic impedance, so you shouldn't have a problem. And I think, one thing that Paul taught me, and one thing that I learned how important it was to really tell the truth to customers. Don't try to hide behind, some excuse. Just be honest and tell the truth. And the customers respect you a lot more for that. Even though there's a problem, they know that if there's a future problem, that you'll be truthful and honest. And that was, it's stressful, but that was a great learning experience.
So what were the type of customers that Brocade had? I mean,
every major server company in the world.
Server companies.
So all of them.
So
IBM, HP, Sun, all the, Dell, Compaq, all the major server companies were using Brocade switches for storage.
So it was
storage area networks.
The application was for the storage subsystem of servers. It
was called the storage area network now. Instead of just having what were called JBODs, just a bunch of disks with the disks all linked up serially with fiber channel, it was more of a network. I mean, you could have subloops, but people quickly learned that one of the problems with the JBOD scheme, it really broke the whole idea. It's like Christmas lights, string of Christmas lights. If one is out, it screws up the whole net. So if there's one ASIC and one disk, which is not playing by the rules, all 127 other disks go down the tube. So people like NetApp, had discovered this problem early on. And so we offered, our price point was, it was good. It was a good price point. It'd be nice if it was a little cheaper, but it definitely addressed that reliability issue. And so highly used by
So another role that you said you handled as hardware director was the EMC testing, electromagnetic, and that's kind of a black art area when often is done by specialists only.
Yes, truly.
What was that like?
That was a real eye-opener. I mean, we, at Sun, we usually had a separate group that dealt with electromagnetic compliance, but I was early enough at Brocade where as a startup, I had to deal with it personally. I mean, I had a consultant and one engineer who was familiar with it. It hit particularly hard because we had one product, the Silkworm 2400, which perhaps the folks there got a little carried away. There's really pressure, especially from Greg Reyes, the CEO, to reduce the cost of our components. And so we actually, Clive Tillman, the head of the mechanical engineering group, came up with a design that had no screws. Let's save the price of a few screws and maybe make assembly. So it kind of clamped together, and maybe that was a avant-garde thing to do at that time, but it leaked electromagnetic radiation like crazy. We would go to Elliott Labs in Mountain View and put it in their test stand, and it was just leaking high frequency, because 2 gigabits per second, high edge rates, little cracks around the frame. It was leaking electromagnetic radiation all over the place. We hired a consultant, I can't remember his name right now, and he was a very folksy type guy, and this was a shocking introduction to me. He comes in with an old tomato can, and he hooks a wire up to it into his frequency analyzer. And he's looking at this tomato can around our Silkworm 2400, and he proclaims, "This is never going to pass."
Yeah, that very scientific instrument.
Yeah, very scientific, a tomato can. And I kind of looked at him and said, but we have to get this to pass because we have to ship this, to reduce our cost and make Greg happy on it. And so I spent literally weeks in the compliance lab trying to learn how to contain the emissions from this board. Now, one thing he gave us advice of doing was something that was counterintuitive to me at the time, was to tie together chassis ground and signal ground in as many places across the printed circuit board as possible. And you would think that would introduce external problems into the printed circuit board. We did that, and it did reduce emissions. You do all kinds of tricks around the edge of the printed circuit board so they don't leak out the sides of the board. I learned that, again, the analogy that I used before on the timing at UltraSpark, you have this box in steel wool and you're trying to push the steel wool in, and you push it here and it pops out there. Well, electromagnetic radiation was like that. If you kind of use copper tape and you paste it all up over here, it comes out over there. So it was like a delicate balancing act. You couldn't be too aggressive on spots that appeared clearly would be leaking spots. You had to kind of average out your use of tape and whatnot to cover holes. There's always a trade-off as well as the size of the holes for ventilation versus will those holes emit electromagnetic radiation. As the frequencies get higher, the holes have to get smaller, and that then impedes the airflow. So there's this dance between those two as well. And so while we were there at Elliott Labs, just mirroring again what happened at Sun, recall back at Sun when we had the diskless boards in the oven and we were getting memory corruption errors on July 4th. We spent all day trying to solve that problem because they weren't going to announce it on July 8th in New York City unless we found the problem. I'm not sure I mentioned that last time, but that's why we were there on 4th of July. Well, this time it was the 3rd of July at night, and we were on the flight path of Moffett Field. And the trainer fighter jets were doing a nighttime 4th of July show this time. So they were coming in right in over our building with giant streamers they emitted the burning streamers out the back. And they were doing a private air show, which we saw. But we were half jokingly that perhaps our electromagnetic radiations might bring down an F-15 or whatever they were. So I thought that was
So was the case design for the product done in-house?
Yes, absolutely done in-house. And so I could go poke at Clive Twillman and say, Clive, you really handed me a lemon here in terms of electromagnetic compliance. But at that point, there were no screws.
Late.
It was late. Yeah.
But were those folks in the room with you when you were
no,
chasing?
just my consultant. Yeah, and then one thing that was kind of fun is while we were at Elliott Labs, maybe not that night, but I ran into Ron Crane. and Dave Boggs, their firm Land Media, their startup called Land Media, was in the building nearby. So I would ask, Ron became kind of one of the analog experts of Silicon Valley. And so I would cry on his shoulder and he would give me some advice. So it was fun hooking up with Ron again at that time. But we did get the 2400 to eventually to pass. What a mundane thing, but an important thing. So I can tell you one more Brocade story, not related to EMC, but again, an interesting tie-in with the people at Sun. So a lot of press and analysts would come to Brocade, and ask, why are you inventing a special high-speed serial link for disk drives when there already is one for networks called Ethernet? And our standard answer would be, well, the reliability has to be much higher. On Ethernet, it's okay for the network to drop a packet or lose a packet because TCP/IP will later come around and resupply it. But you can't. There's too much of a latency in the case of just getting something from storage. You can't afford that. So Fiber Channel guarantees in-order delivery of packets, in-order reliable delivery of packets. You can never drop a packet in Fiber Channel, and so you need to have some type of flow control mechanism. Ethernet never came up with a flow control mechanism. I mean, there are several standards, but they conflict with each other. There's where the receiver will push back on the source, or the source will look at what's happening. So there are all kinds of. But in the Fiber Channel land, you can't draw packets in order delivery. But
because
still,
of latency issues.
And because you want the whole packet to come back quickly. This is storage. You can't wait for
you can't
software
wait
to
like
fix
an
it.
Ethernet. You can't.
Yeah. So exactly. So we felt secure in that sense. But the Fiber Channel guys were trying to broaden their market. Maybe we can use it for workstations, and they're kind of pushing the boundaries. So it's logical to ask, okay, so there were proposals on the table for 10 gigabit per second Ethernet at that time. So the analysts were saying, well, with 10 gigabit Ethernet coming, why would anyone do 3 gigabit Fiber Channel? And I asked them, who's telling you this? Because analysts usually don't make up these questions themselves. Who's giving you this advice? Oh, a well-known and respected angel investor in Silicon Valley. Oh, Andy Bechtolsheim. So I would go to Andy and say, Andy, wait a minute, you're an investor in Brocade. He did invest some amount in Brocade. Why are you telling all the analysts that our technology is going to be defunct with 10 gigabit Ethernet? You're an investor in the company after all. Why are you doing this? Okay. He goes, okay, I'll hold on. And then the next week, an analyst would come in and say, 10 gigabit Ethernet, why are you doing 3 gigabit Fiber Channel? So I got tired of that. So I said, okay, so what we're going to do is we are going to define a 10 gigabit Fiber Channel standard. And so I with the support of Andy and many other people, we started an informal standards body. It was called HARI, H-A-R-I, and we met probably every 2 weeks. So this was the technical people who understood high-speed signaling at Brocade, and technical people who understood high-speed signaling at the Ethernet switch companies. We met every week to define a 10 gigabit per second interface to Ethernet that could be shared by both Fiber Channel and Ethernet. And it was called HARI initially. Some really great experts in high-speed signaling. But we decided that based on the nature of printed circuit board technology at the time, we didn't quite think we were ready to do a single 10 gigabit link. So we had 4, 3, and an 8 gigabit links running in parallel. And that was called XAUI in the end, XAUI. After meeting several months, and I just was kind of just took it ahead of the group. I didn't really contribute from a technical perspective. Kind of kept the meetings under control and stuff. But after several months, we realized that we really had to be meeting in a public forum. It was really against the rules of standards bodies, and so we dissolved and the work continued on the Ethernet, on the Ethernet side of things. And it was announced, and we basically said, well, we'll design our switch chips to use this as inter-switch link. And so therefore, since fiber channel is going to be 10 gig and Ethernet's 10 gig, you can't say, why are you doing fiber channel anymore?
Right.
So
it's a little bit of specsmanship, those two numbers, not necessarily a lot of depth behind it.
Yeah, no. And I'm not sure how important that was in overall for Brocade later, the 10 gig link. 10 gig never went to a disk, so the fiber channel community continued to do 1, 3, and I think what was the next hop, 7 maybe. But it at least got people understanding that there was no fundamental reason why fiber channel couldn't go as fast as Ethernet. And it had this better characteristic of guaranteed in-order delivery of packets. That was the big debate at that time. People were there was like two cultures. There was the storage culture and the networking culture. And the networking people didn't understand the storage culture. The storage culture understood the networking people. And okay. So during this time, the hardware architect, Dave Banks, was beginning development on the next generation, the third generation ASIC, to replace Bloom. And I think we called it Mothra, which was kind of an odd name. But and it was basically higher speed, more ports, working again with LSI logic. We thought it would be a pretty simple thing to do, but it turned out that LSI Logic's new place and route algorithms were not meeting timing, and our schedule was slipping. And it was a little doubly frustrating for me because the team that had done the new place and route algorithms was actually apparently a design team in Russia. So I actually wanted to talk to them because I actually know a little Russian because I took Russian in high school. But LSI wouldn't allow us that level of communication.
And these were employees of Brocade?
No, this is LSI Logic now.
Oh,
Yeah, so LSI Logic was doing our place and route for the chip.
That was in Russia, yeah.
Yeah, and so it's a little frustrating. And they were slipping. It seemed like there was little we could do. I mean, the design was the design. They weren't asking us to change it in major ways. Their place and route software was just unable to meet the timing. So I kept slipping and slipping. I didn't say much about the CEO of Brocade. He joined a week after I did, but he was a very authoritarian, autocratic. General Patton was his hero. Brilliant man. He tended to want to do everybody's job. He would kind of take over from the sales guys and belittle them if they hadn't done well, take over from the marketing guys. He was quite capable, so he could kind of do their jobs and tell them they were not doing well. Very, very powerful person, and I could say a lot about him, but not on the record. So he got pretty upset, and I think he wanted to have some heads roll because it looked like we were about 2 weeks late, 2 to 3 weeks late, and there was going to be a conference coming up. So he was sufficiently angry and supplied enough pressure that I decided it was not tolerable to stay there. And I actually resigned in the fall of 2000. And one thing that happened, interestingly enough, is that the chip actually came back just a month later and worked first time. So, it was off by, I don't know, a month and a half out of a half-year schedule, but it resulted in me leaving Brocade. And a director of software left at the same time as well.
So what is the story? Is Brocade still in existence
No,
today?
no.
So what happened with them eventually?
It's kind of a sad story, and I won't say all of the information. But one of the issues was, Greg was such a brilliant person who could do anyone's job. But ironically, and this is not just me saying this, it's in the record, he didn't really trust engineers. And he had he had a distaste for engineers for some reason, and it's hard to have a startup company if the CEO doesn't like engineers. You know, Sun was very successful because Scott, not an engineer, though trusted the main engineers, but he didn't. He had some mistrust, and that would bother Paul Bonderson and bother other people as well. And then things happened. During this time now, we're into the dot-com era, so the market is exploding, right? And even old Sun is coming back up selling this PARC Center 2000s, and the market is super euphoric, right? The hubris is just flying everywhere. Companies that don't even have products are doing well. Well, Brocade had a product, and it was selling well. And Greg and many of our customers were actually the financial institutions on Wall Street. So when Greg did the roadshows to go public, he was an amazing salesperson. He could just sell your same pair of shoes and your feet back to you for 4 times as much. So people were frothing at the Brocade IPO. When Brocade went public, the stock shot through the roof and continued to shoot through the roof. I mean, so imagine people had shares at pennies per share, and it hit almost $1,000 per share. You unwind all the splits. So after Brocade went public and its stock, we were worth more than many countries in Europe in terms of net valuation. People would say, well, if I join, your stock price is going up so much, my option price is going to be here. It'll already be way underwater, but even every month it was going up, so why should I join? I mean, so Greg, bless his heart, to try to make it more appealing, would say, okay, we'll give you a lower price, like when the first time you contacted us, which nothing was illegal apparently about that. I knew nothing about that aspect of it. But apparently there's some 1930s law that says that if you give someone an option below the price, the time they join, you need to take it as an expense. And apparently the company didn't do that. And so so even though backdating of stock options is not technically illegal, you have to take it as expense. And Greg hadn't done that, and so it became a big court case. Eventually, Greg lost his court case and actually went to prison. And I think that put a damper on enthusiasm. It was a morale hit for Brocade. And in addition, the market for fiber channel was a bit expensive, and people were desperately looking for other ways to include storage and not have to purchase a storage area network. So they eventually got bought, I think, by Broadcom, and long history. And I think the original Brocade is just on support now.
Mm-hmm. What about the fiber channel product? Or did that survive?
It survived because they probably had a few customers and they had to continue supporting it. And then InfiniBand came along, and InfiniBand was kind of like fiber channel done better. I mean, InfiniBand was really designed for high-end supercomputers to link together processors, but since it also had in-order and reliable delivery, it could be used as an interface to storage subsystems as well. But the storage community didn't jump on it right away. But anyways, it gave another set of things for a switch to do. So you could maybe combine InfiniBand and fiber channel and maybe even Ethernet. And so there's all kinds of technical things the future Brocade company got itself involved in, but they didn't pan out in a big way. But so I was gone though.
You were gone by then. Yeah.
I mean that 2 years was very intense, and I really actually did enjoy it, even though there was this issue of attention between the highest levels of the company in engineering. It had great people. I mean, manufacturing people, support people, software people. It was a fun place to be. So I took some time off. During that time, it turned out that Andy actually asked me if I wanted to be an engineering VP for his next startup, Kalaya. But my wife, she probably didn't say exactly these words, but in my words, it was kind of like, well, if you might want to get to know the strangers in your house, you may want to consider not going to a startup company. So I thought, okay, maybe it's time to get out of the startup fast lane. And auspiciously, above the hill, just a few miles from where I live, is the IBM Almaden Research Center. So I thought, that might be a fun place to work. So I called up my friend Winfried Wilkie, who had been the VP of Engineering at HAL. Remember I mentioned HAL, and we had met up via hot chip conferences. HAL, remember, had started to build SPARC chips and SPARC workstations, SPARC servers, and so we naturally got to know each other. And he was then at IBM Almaden, and he didn't want to do a startup for personal reasons. He's Anita Borg and his previous wife had serious health issues, which I won't go into here, but so he was willing to just stay at a place like IBM Almaden, which is a place where you could really follow your nose and not have to necessarily follow somebody else's roadmap. You could create projects that hopefully would be of interest in the marketplace or to IBM as a whole. And I called him up, and he had this idea that he wanted to develop this really exotic server, something you never would have thought of yourself. Winfried's background was in particle physics, so he was a physicist, and as a physicist, you're used to being around novel thinking, large-scale experiments, and big things. And IBM certainly had those type of people in research, and so Winfried was right at home. So he had this idea that he wanted to build a very different server. Servers traditionally are little, what are called 1U, 1.75 inch high, 19 inches wide, 18, 24, 36 inches deep servers, and you plug them into a rack and you plug your cables in, there's a switch on top, and there you go. It's cookie cutter. That's the way servers are. I mean, you can get bigger servers, bigger than 1U. If they're multi-processor, there'll be 6U or 8U high. IBM certainly specialized in those. But Winfried's vision for a server was you would build the server more in a compact brick style or cube style. So maybe, 4 inches on a side, 6 inches, so 6 by 6 by 6. And you would stack the bricks, and they would communicate on their surfaces.
Without cables.
Without cables. And so they would just push two together, and a network connection would be formed between those two. And since you have a lot of them, maybe you have 10 bricks by 10 bricks by 10 bricks. That's,
So they were connectors on the sides?
Well, I'll show them. They were either capacitive or inductive.
Okay, not a physical connector.
Not a physical connector. The idea is that physical connectors are a bane of the industry. Yeah. I learned a lot about physical connectors during this time. Traditional physical connectors, you want to put, a recipe that works is gold, nickel, copper. You put the gold on top, which is a little soft, but it resists many contaminants. Nickel is hard, and copper is a good conductor, and hopefully that layer will last as long as your product does. Throw all the insertions and deinsertions you want. But how many times have you had a problem with a connector, right? And so the thought is to, instead of having a mechanical connector, which involves force, right? There's usually the terminology engineering people use is a male and a female plug, and they have to be inserted into each other. So if you have a box, if you want to have boxes that slide into place, you just put one down, put another one on top of it, put one beside it. You can't be plugging them into each other, unless you had an explosive charge that connected them. So they have to, and if you have two metal surfaces that are brushing, there may not be enough brushing to wipe away surface contaminants. So the idea was to have, I think Winfried's first idea was inductive, and I said, no, inductive things are slow. Let's go capacitive. So I designed the capacitive couplers, as we called them. So anyways, his overall vision, 10 by 10 by 10, that's 1,000 already in a small space. 20 by 20 by 20, you're talking about 10,000 things in a pretty small space. So it's extremely dense. So now the question is, how do you get the heat out of the middle? So, since you might think of a nuclear reactor, right? Nuclear reactor has rods, and so you would cool it via cooling rods, and the bricks would slide down over the rods, and you would cool it that way. I have a picture we'll show in a minute. So this was his vision, and I was like, that's a pretty crazy vision. They're going to let you work on that? Yeah, in research you have to have a really outlandish idea. You just can't do something more traditional because that's what development companies do. So I was new to research, so I said, okay, I'll go along with that. I mean, the world has moved away from liquid cooling. Keep that in mind. But he knew of other liquid cool projects, and IBM was the last bastion of liquid cooling, in its high-end S360 machines. In fact, they'd gone to minus 10 degrees Celsius cooling in the 360 successors. So I said, okay, I'll do that. And I couldn't beat the commute, a bike ride at 500 feet up hill, but still I couldn't beat. So in May 2001, I joined the Almaden Research Center as a member of the technical staff, which is actually a title that applies to a wide range of salaries and people. It's just a broad category they have.
Not a manager, in other words.
Yeah, I didn't start as a manager. There was really no management opportunity there, really. So it was getting out of the fast lane and getting back into doing technical stuff. One thing that was true was that I'll never forget my first day. I pull into the parking lot and there's a sign that says, "Did you remember to turn off your car lights?" And I go, how paternalistic is that? They're asking me whether I forgot to leave my car lights on. I thought that was really crass. But anyways, I soon learned that many of the researchers there really enjoyed biting back at the hand that fed them. It wasn't like everyone was trying to be a conformist, but it certainly research was trying to be the avant-garde corner of IBM corporate.
What was the dress, just out of interest, IBM was always known as the white shirt and tie
certainly
company,
not
by then. It wasn't.
No, they threw all that out in the mid-90s.
Okay. So
I think the marketing people for sure, but
yeah, but that's
but as the engineers, that all
typical Silicon Valley.
I mean, it started at Xerox PARC, I think. We wore blue jeans and stuff, and that kind of spread around Silicon Valley, and I think that eventually made its way to the East Coast.
Even there, yeah.
Maybe not T-shirts on the East Coast, but yeah. So certainly people at IBM Almaden were more casual. The research was, you think of research as possibly being frou-frou, but the reality is that IBM Almaden Research was directly connected with the disk drive development. So they were responsible for the next generation heads. Disk drives had become a massive business for IBM. In the mid-'80s, I don't know if I mentioned, but the 3380s, the giant disk drives, became the second largest selling merchandise in America behind airplanes. They were making billions of dollars selling disk drives in the mid-'80s. So keeping then of course the whole ecosystem of disk drive vendors started. That's a whole history. But keeping that roadmap going was important. And so IBM Research, the research center on top of the hill, Cottle Road was the facility down off Highway 85, 400-acre site with massive buildings, manufacturing buildings and whatnot.
But totally separate part of the organization. In
separate, but they were linked because they were expecting the advances to come in the lab on the hill. So there was a huge science and technology presence at IBM Almaden Research, and it was still going on when I joined. So I could go down to Cottle Road and see, the advanced research being done. I could see how they were, for example, how they would try to measure the bit error rate. 1 bit error in 10 to the minus 15 accesses. How do you get numbers like that? And the experiments they would do to try to show that level of reliability. It's just a fascinating place to be. And high-speed signaling that had to go on. You're getting up into the gigahertz speed on the heads. The head heights are measured in angstroms, several atoms. So there was just a really vibrant connection between IBM Almaden Research and the disk drive development area.
So how did they end up, so IBM you think of as an East Coast company, how did they end up having these two major divisions in Silicon Valley because of Silicon Valley?
Well, I actually know some of that history because I did with my involvement in the Computer History Museum, I did a lot of history on the RAMAC development. So in the early 50s, IBM on the East Coast found they couldn't hire engineers fast enough. And they couldn't recruit them from the West Coast because no one wanted to go live on the East Coast. So they intentionally set up a research lab in San Jose in 1951, 52. And they intentionally wanted to recruit from Stanford and Berkeley. and plus whatever industry people still might be on the West Coast. So they set up the lab in San Jose. They're on the building is still there on, I forgot the name of the street right now. They gave an blank open option to just figure out how to improve data processing in companies, and they did all kinds of experiments. Eventually they came around to a disk drive. Someone at the National Bureau of Standards had thought of an interesting way to do a disk drive. You take a book and you put it on a table with its spine up and open up all the pages. Imagine you could have a head circling around, and then, so instead of pages, you have a circular disk. You would kick it, and the head would read that read that disk. So that's what Rabinov had done at. Oh, you know this guy.
I know Rabinov. I knew Rabinov.
This is the amazing part of this story: is Roy Ogus, actually knew this guy, an inventor at the National Bureau of Standards. Yes. So he built a prototype, but the guys in San Jose thought it was impractical, and they had the idea of just putting 50 disks on a single rod. And it's kind of a diversion, but so they were successful in inventing an important device in IT technology, the disk drive, the very first one. They developed a machine called the RAMAC for it. But, the IBM 1401, which had been developed on the East Coast, kind of took over the market as a stored program computer. And so they had to shut down their CPU development in San Jose, and they just supplied it as a peripheral. So IBM computers, the 1401 and the 360. So that's kind of why IBM doesn't have a big presence in Silicon Valley. All they really wanted from that whole effort in the end was the disk drive, not the system. So there was really no impetus to build a systems group in Silicon Valley for IBM. So that was interesting history to discover.
Yeah, that is an interesting story.
Yeah. So here we are, back in the year 2001, and the project was going to be a combination of software and hardware, because if you have all these bricks, those are the small cubes, one can die, obviously. And so what kind of reliability, what kind of redundancy are you going to build into the storage code? Simple replication could work, but now you doubled the cost of your storage. And erasure code across many bits, perhaps 8, perhaps more. So that way, if one brick goes, you can rebuild the data from the surviving bricks. So we had to develop the software as well. So there was a project started called Turtle Farm, and it endeavored to do this, but not sufficiently staffed, and so it wasn't really successful. There was already an ongoing project that had started at IBM Research called the GPFS, General Parallel File System, started by Roger Haskett and people in the late 80s, actually. It actually started as, this is hard to believe today. Given today we can pull out an iPhone and watch a movie on it, or watch our movies on our laptop, but in the late 80s, a single CPU, if you remember, did not have enough performance to deliver a video stream that you could watch. It's a little hard to imagine now because we have gigahertz processors and we pull up, we watch videos on our phone, but a single high performance $10,000 CPU couldn't source a single video. So the Sun and SGI and many companies at that time were trying to come up with a video server that would use multiple servers to supply a single video stream to the user, perhaps in a hotel, maybe someday at home. And IBM Research, Roger started a project to design such a system. They did design such a system, it worked. But being researchers and generalists, they designed a general parallel file system that could both read and write, so it could be used by supercomputers, not for video streams, but just for storing data. So it automatically stripes the data across all the disks. The keyword is automatically, right? So you have a large file system. GPFS will take chunks of it and put it on each of the disks connected to servers. Multiple servers, multiple disks per server, just stripe it across all the systems, and then any given client can now be getting bits from multiple sources. So Roger in the early 90s went to the software groups in Poughkeepsie, New York, and there was a good matchup. The supercomputer groups there needed a high-performance file system. So Roger established this channel to market for GPFS, where if IBM was selling a high-end supercomputer, multiprocessor supercomputer, you would likely get GPFS along with it for free. So he wasn't selling it as an unbundled product, but it was being sold with like RS-6000 multi-computers. So, and then by the time I joined IBM, they began to sell it as an independent product, so it could run on not just on AIX, but it could run on Linux. And it started to sell in the open market. So GPFS was this huge high-performance parallel file system organization and culture that existed. And that was one thing we could run on IceCube. And we ended up doing that, in fact. We actually ran it on IceCube because we were unable initially to get that distributed. The software folks were unable to get the erasure encoded software to work. So we just demonstrated the GPFS.
So just to set the context, when you joined, what was the state of IceCube? Was it a concept or had
Purely a concept.
So that nothing had been built yet?
Nothing had been built.
But he was thinking of moving forward on it.
Yeah, so he asked me to help basically make it happen. And so, you know, I'm used to implementing things. So I brought to the whole endeavor, you know, the knowledge of how to build this system, how to work with Silicon Valley companies to get the printed circuit boards built. We worked up with Harold Jules in Wilmington, Germany to they actually manufactured the mechanical parts. I'll show you some pictures in a second. They took responsibility for the central processor card, the CPU card. I designed the network switch card. They designed everything else, the memory card, the CPU card. I linked up with Silicon Valley manufacturing firms to manufacture the boards. One thing that was true at IBM Almaden Research is that since it wasn't a traditional systems company, they didn't have really technicians or a staff to build things. There was only one really technician, Manny Hernandez, who helped us a lot. But we ourselves had to build these things. I mean, Harold Jules and his team in Germany, you know, did some of the design, and I had firms in the Valley manufacture the boards, but we had to, you know, and they stuffed them with components, but we had to assemble them all. So it was a very hands-on experience, so it probably took longer than one might imagine. I have a picture here of IceCube, so that will help. So, well, that's me, and that's Winfried Wilke, and that's, I forgot his name. So here's the IceCube. We built, as a prototype, we built a 3 by 3 by 3. And on one side, we connected traditional 1 gigabit Ethernet, so you could basically get everything on one face. And we had a cute little LED system where you could see which way the lights would blink depending on which way the ports data was moving on the ports. These towers, you see my hand is on a tower there. That was actually my idea how we ended up doing this. The towers, they're aluminum extruded, rectangular cross section that go through the bricks, and they fill with water or liquid coolant, water plus glycol, and there's a little overflow valve at the top, so they naturally fill up a certain level and then go out the other side. So this is a liquid cooled system. The cable's on the floor over here to liquid water from the building. So it was very quiet. The IceCube, even though this is 27 servers,
No fans or anything.
There were no fans. And so you could be in a room with 27 servers and it was quiet. It was like a bubbling brook. We really, really liked that feeling.
Underneath it is just a stand? Or
Yeah, this is just a stand, and there was just some lab control equipment where you could turn power on and off individually to the brick. So one of the ideas is that if a brick failed, you could disable its power. Thereby, it wouldn't, be boisterous and screw up the network or something. So you could turn off a brick.
So how did the power connections work?
The power connections were actually connected. Yeah, they're not visible in the picture either. There's actually a what are they called? Hidden connector between the top and bottom. So power went vertically. So each brick has a power connector between the two.
And that's a real connector.
A real
not
connector.
a capacitor.
Yeah, because you're just placing the bricks down vertically.
Okay.
And
so the one in the real middle, it gets its power from the adjacent ones.
No, vertical. They're vertical. So it gets its power. The one in the middle gets its power. Yeah, people would always focus on the one in the middle, right? What if that guy dies?
That's the most isolated.
So we would kill the one in the middle, and Claudio Fleiner wrote the software that does all the routing. Ethernet traditionally wants to find one path through the network, right? This was an innovation actually during this time. The idea of an Ethernet having multiple paths through a network, all converging to one destination, wasn't allowed by Ethernet. So we changed the Ethernet routing protocols so that you could route through different paths through the cube. One thing that Claudio did as well is, since we were basically building a PC, I was a little shocked to find that we needed access to the BIOS because we had our own devices and stuff, the switch. And that's not a simple thing to do. To get access to a BIOS, you have to have a license, and it's all top secret. So we were able to do that, though. We were able to get a copy of the BIOS and modify it, which Claudio did.
So you said it was liquid cooled?
Yes.
So was there a plumbing system?
Well, that's what I was describing. There are these towers. I should have brought one. You can see these aluminum. See that aluminum thing right there?
Yeah.
That's a 1 inch thick by 6 inch wide by however tall you want tube, but it's rectangular cross section, filled with water, liquid, and then there's a return tube that goes up through it, and so the water fills it up and then goes back down through the return tube. Okay. And so that provides a cooling spot. And then, here, let's look at an individual brick. So here's a picture of a brick. So it's a little hard to see, but there's the opening for the tower right there. And so all the electronics is on a piece of aluminum with heat pipes that go over to the aluminum. And so then when the brick goes on, this was really clever. Winfrey came up with this. When the brick goes on, we have a little lever, these two levers that we would rotate, and that would apply pressure between the vertical column and the inside aluminum plate. So we'd get a high pressure. We had to have a thermal material between the two because metal to metal is not that great of a thermal contact. So all the heat then would go, in fact, you can see a heat pipe. It's a little hard to see, but there's a heat pipe right there from the processor chip over to the plate. I think we had 2 heat pipes. Our DIMMs did not have a heat pipe, so that was kind of cheating. So IBM had great, do we use IBM software? Yeah, IBM had, or we use a company's, I can't remember. But a great thermal simulation software so we could simulate the thermals inside this closed box. And we could see how warm it got, and we actually had a thermostat inside, so we could always measure the temperature inside all of our
So every cube had that tower with the cooling. So the one in the middle again had its own cooling.
Well, there's one tower that goes vertically through all of them, right? And each brick clamps up against it. So one tower is shared by, in this case, 3 bricks. So so there are 3 by 3. There are 9 towers.
9 towers, yes.
Yeah, and all the bricks on one tower share the cooling in that tower. So we could measure all the thermals and saw that it worked just fine. We could measure the CPU die temperature because the dies now have thermistors on them. So it all worked. The only cheat, so there was one other cheat. So the disk drives, we had 12 disk drives, 2.5 inch disk drives. This is one. They were all packed together side by side, and the heat was conducted up to this aluminum plate over to the aluminum bar. And we actually could get the disk drive temperatures as well because they have thermistors in the disk drives. So it actually worked, but I'm not sure how scalable it would be going forward. It might have been. I think probably the biggest difficulty would have been in the DIMMs. I mean, IBM, I'll talk about that in a second, did this amazing liquid-cooled system I'll talk about in a minute. But this was very obviously non-traditional. You've never seen a computer like this. So I had fun bringing people into the lab and showing them our three-dimensional computer. So the nice thing about it is, if you add a brick in it has storage, it has a CPU, and it's a network switch, right? So it's a scalable unit. So you're actually building a scalable switch. Each time you add a brick, you've added more ports. And you've added more CPU, you've added more storage. So it's a naturally scalable system.
So are the disk drives, I understand this is a switch really.
Well, there's a switch in each brick, and
Right.
the disks talk to the processor.
But is the disk the storage you are managing, or is the disk just a disk for the local software to run
It's the
on?
storage we're managing. Yeah, that's a good question. We used not a PROM, flash for the local boot device, for the local processor. We just use a flash chip.
Okay, so the actual storage being managed is part of the cube, in other words.
Yeah, so the software then would manage the distribution of all the data across all the disks. And so we tried with Turtle Farm to actually create new software which would do that. Later we had an effort called Kubos, but I'll talk about that. Well, I can talk about it now. That was a second generation attempt called Kubos to do the distributed erasure coding. I mean, at the time, places like Google were starting to do this naturally in their server farms. We just had a small group here, so.
Right. And what's the order of magnitude of storage in a 9 by 9
Well,
block?
there are 27 times how many disks? 12 disks. So that's over 300 disks. So whatever capacity you want to put on a disk drive today, 2.5-inch disk drives are quite large.
Yeah,
They're
well, today would
20
be a huge amount
gigabytes.
of
Yeah,
storage.
these were just. It would have been nice to have used flash-style disk drives at the time, but at this time in 2004, 2005, they were kind of expensive. So we still used mechanical,
rotating
what we call rotating rust
Yes.
disk drives.
And what about the software? Was this all custom software?
Well, that's what I was saying. Turtle Farm was the project the first project that tried to do the distributed erasure code and storage. That didn't pan out. We ended up demoing the system with GPFS, which was very reliable, and the whole team supported it at Almaden, but it was based on replication. So for our demo, what we did actually is we hooked, since we had external Ethernet connectors, we showed a movie, a Ben-Hur movie, and we were streaming it from multiple disks. GPFS does that. That was the original motivation for GPFS. Then we'd kill a disk, and you'd watch the movie, and you'd watch that nothing happened. There's no blip.
So it was really redundant.
So
yes.
it was real time.
Yeah. And what were the processors in there? Were they just
Intel,
standard?
these were 80,
Intel.
these are Pentiums,
Okay.
low power Pentiums. I
And
can't remember
so
which one.
what kind of operating system was the software running on?
Linux.
Linux. All right. So
Yeah, these
that's
are Linux boxes. Yeah.
Linux boxes. Okay.
Yeah. And it was fully functional. I mean, it took a while to get it built because we had to hand assemble. I have pictures of us hand assembling these bricks. First you have 6, then you have 10, then you have 20, then you have 27. we had to set up our own manufacturing line basically in the lab to hand assemble these things.
Right, and the picture of the individual module, is that entity on the right? That's the capacitive.
Oh yeah. So let's talk about the capacitive coupler.
coupler?
So here is the communications board that I designed. It would all fit in one chip today, but this is 2003, 2004. So this is the switch chip. This is a Broadcom switch chip, 8-port switch chip, and this is just to convert to 8 1 gig. These are 8 1 gig ports. This converts to 1 gig serial over twisted pair for the external face ports. And so there are 6 sides to a brick, right? To a cube. So there are 6 capacitive couplers. 1, 2, 3, 4, 5, 6. So top, bottom, left, right, front, back. So each coupler, it turns out this is the XOWI interface. There are 4 channels. These are, yeah, maybe I forgot to mention, this is, did I say 1 gig? This is 10 gig. 1 gig outside, 10 gig inside. So these are 4 channels, each running at 3 1/8 gigabits per second. So this is the receive side and this is the transmit side. So
and its friend on next to it was exactly over it.
It's exactly over it. So that
form a capacitor between.
Yeah.
The two
So
of
the
them.
transmit side talks to the receive side over here. All they have to do is touch, and you have your connection.
And you have a capacitor there, and that's why
there's a capacitor. But that's one of the mysteries of physics as to how signals jump. You know, it's called the displacement current. If in physics class, no one really knows what it is. Some kind of near field effect. Where the signal just magically goes through the gap. And so this is ceramic, and it has to be polished to a certain smoothness to guarantee a minimal gap to get the capacitance, enough capacitance.
So what kind of gap was there in physical terms between the two?
Yeah, it was measured in microns.
Really? They could get micron?
Yeah, like
distances?
10, 20 microns. Yeah, I'll have to
okay.
look at my notes to get that number. Yeah, you'd polish it. And
so they were pressed together by force, or?
Well, we had a very clever idea. I think somebody on the team came up with it. I didn't bring the holder, but you can see in the picture there's a plastic holder around them, and then there was a light spring, just a piece of metal, and so the two would come together. There'd be bumps and holes on the plastic part, so the bumps would naturally find the hole of its partner, so they would perfectly align and mate, and the springs would hold them together.
Okay.
And we kind of wanted, this is ceramic, and so you can break ceramic, and so to make it more robust, we also explored we designed a capacitive coupler based on mylar, and we had that working, but we didn't ever ended up building it. So mylar would be, and you'd probably have a pillow behind it. It would kind of push against the other one. The other thing we did is IBM had great high-speed simulation software. So we used that to design the connection on the back, and this is where you learn a lot about the effects of inductance. I mean, this is a differential pair. That small opening is enough to affect the signal quality. And so we actually designed a 10 gigabit serial link, so you could have 4 10 gigs, and in simulation it worked. One thing that's nice about this is we didn't have to modify the drivers that drive the 4 lanes of 3 gig. The distortion that this provided was within the compensation capabilities of the existing chips. I mean, if you had full control, you would redesign. I mean, the fact that our serial lines work at all is amazing. If you've ever looked on a scope at a 10 gig serial line, or the lines that go to memory chips, or it's all a jumbo. because you can have many zeros in a row or many ones in a row. You get different frequency components. So you have high frequencies, low frequencies, and so they respond differently to the network. And so you end up, when you have a low frequency, through a capacitive thing, it starts to decline in value, right? And short things are really fast, and so you have a precompensator which gives more energy to the low frequency components and less energy to the high. You have receivers that it's quite an art, the whole serial transmission and reception process. But luckily at this time, and with this design, we didn't have to worry about that. And the paper shows eye diagrams that show. Crosstalk was a little bit of concern I had at the higher 10 gig rate, but this worked fine. We had no problems. So even though it's wireless, there are wires inside. I mean, this was a very high-speed connector here that we were able to use to connect them to the board. So it worked.
So let's see. So you said when you started it was a concept, and then you eventually built some things.
Yeah.
And you had prototypes.
Yeah. And then what?
That's the question: is what happened after that?
So it made for good PR, but some people think that research is just a branch of the marketing department. I think that's true in many ways. But we really did want to turn it into a product. So, I guess, but in terms of dates, 2005 is when we had this working. So we did demo this to many customers. We have this working thing with water flowing through it, right? I mean, it's pretty impressive. You bring people in the room, and they go, hey, this is cool. I want one of these. In fact, this man who was head of a large Japanese bank wanted one for his bank. And so we were almost ready to build another one for him. That was pretty funny.
Did you make any that were bigger than 3 by 3?
No, that was so much work. You would need a team, a company, a startup to do that. And it's expensive. But during the demos, our Marcom person at Almaden would bring companies in, and they would go, yeah, this is really cool. When can we have one? When can we get one? What people liked about the idea was that it would run for a long time, kind of like Tandem's nonstop idea, right? We said that if bricks die, it keeps going. And you might over-provision it a certain amount. You can predict the failure rate of disks, so you over-provision by 20%, and it should last 5 years without having to touch it.
How many failures could it tolerate? How many failed cubes could it tolerate?
Well, yeah, we did a lot of research on that. In terms of what happens to the network, how long can the network stay up? What percentage of bricks need to fail? So we had equations and graphs and papers and simulations. And so if you over provision, and then if you didn't over provision enough, you could always just add more bricks, and bricks of higher capacity, could perhaps be added, but that was not a feature that software could handle anytime soon. People would come in. One person was really listening to one of the demos. I was impressed. I think he was a high school student. He said, now wait a minute. You're saying this thing will run forever. You have to over-provision the number of bricks. Aren't you basically putting the burden on the customer to pay for your unreliability up front? Yeah, but that's reality. So his point was, if you thought about it more, was that you wouldn't want to deliver a whole bunch of bricks that had low reliability, because then you just have a pile of dead bricks. So that would bemuse you to perhaps produce more reliable bricks to start with, which might imply you have to do burn-in. And IBM had abandoned doing burn-in years ago, and many companies have. Companies used to do burn-in, a good way to test the resiliency of the components and then ship them to the customer. But with improvements in manufacturing, it was easier to just ship it to a customer and then deal with the problems later. So most of IBM had already abandoned burn-in. So that was one of the negative sides to this idea, is that you would have to have more reliable manufacturing, so not to overburden with the redundancy. People love redundancy, but they don't want to pay for it. But I think what our story there was, though, is since storage increases in size so quickly, you can just add bricks. So, and whatever's failed, so what? We'll just add more, because you want them anyways, because they're higher capacity. So it was a reasonable start. So now the question was what to do with it. So one thing that happened is there was a person. Well, we talked to the storage people of Tucson. They weren't interested. Other parts of IBM weren't interested because it might compete with the Blue Gene supercomputer work, although we were a long ways from being a supercomputer.
That's kind of interesting that IBM itself didn't seem to be that interested in using this.
Yeah, well, IBM was trying to move to using more off-the-shelf stuff, and here's this new, again,
which they had funded, yeah.
Well, IBM had done so much internal stuff for so many years. There was really starting to be motions of hardware's becoming commoditized. Let's try to use off-the-shelf stuff. Why would we want another system which is defined strictly by us and isn't second sourced by anybody? I understand that coming. So the question was what to do next. And in early 2006, happened to be that a VC from East Coast VC firm called New Venture Partners, Frank Romalowski, was kind of bantering about inside IBM. Their model was try to find a lone researcher who had a great idea for a product, but he couldn't bring it to the market because the volumes wouldn't be high enough for IBM to justify productizing it. Take that, spin it out, make a successful company. So he found our project. Now, the only problem or challenge with our project is it's not some simple thing as it's on a shelf. It's a whole systems product with software, hardware, and everything. It's a big enchilada. And but he was willing to take it on. So by October 2006, with funding from new venture partners, we started a spin-out, a startup company. We called it Seval Systems, S-E-V-A-L. I didn't like the name for reasons I won't talk about, but they gave us $5 million or something, I don't know. But since we weren't sure if it was going to be successful, and IBM was resisting it as a spin-out, we remained IBM. 5 of us remained IBM employees and worked there, and we hired about 6 people or something. I can't remember the exact number. We hired 5 employees. So 5 of us joined as IBM employees. We hired 5 employees.
And the 5 that were hired were not IBM employees?
We're not IBMers, no.
They were Seval employees?
Yeah. And we had, a board. We had met with the VCs, and we changed the design. This design fundamentally is too expensive. Manufacturing costs would be just way too high. So I changed it to more of a blade-based design. So you had processor blades, you had storage blades, so now the processor blades could fail independently of the storage blades, and a 2D backplane, not a 3D thing. And in 2D, we had 20 port switches on the CPU cards. This is on paper now. We never built it. And actually, the reliability of a 20-node network is much higher than a 3D because you can skip over nodes. If you have 20 ports, you don't have to go just to your nearest neighbors. You can go to your nearest neighbors and their neighbors. And so you get this very rich network. And we did simulations on that to show it was much better. And then the IBM lawyers insisted that we remain liquid cooled, which was a hindrance, obviously, because the world's moved away from liquid cooling. But I realized we could build a large rack and do a liquid to air heat exchanger on it. So we could have air moving through the rack, through the blades. And this was standard technology in the various cooling companies out there. And a air to liquid heat exchanger, and then a water connection on the side. And in some sense, this was mirroring what was happening at companies like Microsoft, building the big trailers full of servers, a water connection on the side, but air inside, and an air to liquid heat exchanger inside.
It's interesting you said the lawyers wanted you to retain.
Oh.
Why would lawyers have an opinion on that?
It was hideous. IBM has really no track record of spinning out companies. Some companies do a great job, like Cisco did. IBM hated it. Lawyers were really worried about sullying the IBM name accidentally. The terms of the spin out were just onerous. I mean, they were, IBM would get the first right of refusal for anything that might happen to the company. If we hired like Osama bin Laden, they would be able to roll back and pretend like they had nothing to do with it. The fights with the lawyers were endless, and that was one of the problems. So we went to Sand Hill and we pitched it to all the VC firms. I even pitched it to Mike Boych, who was now at a VC firm up there, my high school buddy, who I had run for freshman class president with and lost in my high school.
That's right, I remember that.
He was kind of interested in it, but the only person who really bit was Bill Joy at Kleiner Perkins, and the other person there, I can't remember right now. So the database guy.
Yeah, I was just commenting, you said the lawyers wanted it to be water-cooled, to remain
Yes.
water-cooled.
Yeah, because I think Ice Cube was, so why give us more freedom?
So it's probably from a risk point of view that they were...
No, I think they didn't want us to be successful.
Oh, I see.
Yeah, that was,
they
they're
did have
so
a
onerous, it was
technical
so
motive.
hideous that they're,
Oh, okay.
I never asked them, but, well, you're spinning on Ice Cube, well, Ice Cube's water cooled,
Okay.
I was certainly willing to move away from water cooling, the whole industry was. So we had the startup. We started to work on this air-cooled with a air-to-liquid heat exchanger idea. All the simulations, the cooling simulations look good.
And you call that ice rack,
We called it Ice Rack. Yes, I didn't bring any pictures. We didn't build it, but we had lots of drawings. And then the racks would have a top of switch rack, which would connect to the other racks. And so we had a very low hop count. We could have an array of 10 by 10 racks, 100 racks, each with, well, variable number of servers. The number of servers and disk drives were adjustable, so you could have a disk drive rich server or a CPU rich server. So you could have anywhere from 20 to 50 CPUs, and a very low hop count because each node has a switch. So maybe a hop count of only 5 or 6 across 10,000 processors. So when we went and talked to companies like Microsoft and other companies, they were really fascinated from the network perspective, building this scalable network switch. But, Bill Joy said, okay, let's give it a shot, but he immediately checked with his buddies at Google. And Google was just then starting to build out their large data centers. And to be honest, they didn't need the help of any startup. In fact, later Google built their own switch chips. And what was interesting is already Google this was very educational for me and for us, was already building data centers with power usage efficiencies, PUEs, of 1.2. In other words, for every kilowatt of powering electronics, they only needed 200 watts of cooling energy to cool it. Most PUE numbers in data centers are closer to 2.0, twice whatever energy to run the servers. You need that same amount again just to cool them. That's a pretty inefficient, but that's kind of standard in the old Liebert data center rooms. They had already figured out how to do PUEs of 1.2, and they were publishing them. It turns out that figure was about equal to what our number was. So the advantage of liquid cooling was gone. So the way Google was building their large data centers, they hired large industrial designers, and you basically build a data center with pretty reasonable racks, high ceilings, and you pull in outside air, pull it through, and push it back out to the outside. And you can't get more efficient than that. There are intermediate schemes where you have air-to-air exchangers, but if the climate is good, not China, let's say near an industrial plant, pull in outside air, pass it through your servers, run at pretty high temperature. The temperatures might get pretty hot, especially up high in the ceiling. In fact, I would go to server cooling conferences, and everyone would notice I worked for IBM. They'd come up and ask me, how hot can I make the outlet temperature of IBM servers? And I would say, don't ask me, because everyone was pushing the envelope, realizing that you could run them hotter than the old standard set in the 60s and 70s. With these air-based systems with no Lieberts in the room, you could get away from those cold, and save a lot of energy. So there was really no reason to do a liquid cooling based system. And so we, based on the fact that the acquisition terms were onerous, and NVP owned too much of Saval, something like 70%, it wasn't appealing to VCs. In July 27, in lieu of a second round of funding, we just elected to shut the startup down. In fact, one VC we were talking to, Forrest Basket was one of the VCs we talked to. One of the VCs, while we were pitching to him, he got a call about how they were shutting down Rackable. And he goes, well, this is bad timing, isn't it? So the whole transition was occurring where the major data center infrastructure was being done by the large companies, Facebook, Google, Microsoft, and no one needed the help of a small company.
So it was a complex set of reasons. It was certainly not just pure technology.
Yeah, but that was a factor. We were still, because of liquid cooling, a little too expensive.
Part,
yeah. But even if you took that away, I think no one wanted
like
the help
the onerous
of a startup.
acquisition terms would
that
go
was
away. Yeah.
Yeah, no one really needed the help of a small company.
Yeah.
So, okay, so at that point we shut it down, and so Roger.
You all went back to IBM.
And we technically never left. So five of us.
But the ones that were hired,
they
went back to
went and
IBM.
found other jobs. Well, they didn't work at IBM. Remember, they just went and found other jobs.
Right. They were working for Saval, and they were out of a job then.
Yeah, they just went and found other jobs. So I, at that point, was thinking of leaving IBM, but Roger Haskin, who was the godfather of GPFS, who I've talked about before, asked if I could manage a new project to deliver exactly the software we had needed for IceCube, which was a way to distribute all the data across all the disks. And if a disk fails, an erasure code would, distributed erasure code would bring you back the data. Declustered RAID, as it's called. It had first been pioneered in academic papers in the early 90s, but there were really no implementations out there yet. So this was pretty exciting, I thought. There already was an architect, really a brilliant man. Another case of one of the brilliant architects of Silicon Valley, Jim Wiley, who had been at IBM Almaden his entire career. He was a lifer IBMer. Brilliant man, brilliant programmer. When I say brilliant, I mean truly brilliant, equal to 3 or 4 people. Normal programmers were just astounded at what he could accomplish in one day, either through writing software or writing specs or understanding problems. So I said, sure, I'll manage that project, software project. I named it Perseus for the Greek god that could slay sea monsters.
Okay.
And the funding was initially coming from DARPA and a project called PERCS, which was just the name of the next large supercomputer they wanted to build. And IBM had been awarded the contract, $30 million or something, and some number of million could go towards development of the storage system software. And this was the last huge liquid-cooled hurrah computer probably from IBM. This PERCS machine, the architect, I'll fill in his name, designer of the hardware, this was the type of machine that you would find in the basement of the No Such Agency or in a Dan Brown Digital Fortress movie. It was liquid cooled. The racks were 1 meter wide and 2.5 meters deep. Each rack could accommodate 180 kilowatts of heat with 1 gallon per minute liquid cooling per rack. The anticipated cooling for the entire 90 racks was a water pipe a foot in diameter. Each processor board, a meter wide, 2U high, had 8 multi-chip modules for power processors and 8 multi-chip modules for the interconnect, which was a star network. So every MCM could connect to every other MCM in the entire cluster. And the storage units were 1 meter wide, 4 high, with 384 2.5-inch disks in it. And I suggested they have an air-to-liquid heat exchanger in it, which they did. Initially, they thought they would try to direct cool the disk, which was crazy. If you had to ask how much this system cost, you couldn't afford it. I mean, one of the list price for one of the storage drawers was $500,000. Now, they sold it probably for less, but that gave you a sense. The list price for the processor modules were close to $1 million per processor. The world had moved away from liquid cooling, a heavily liquid-cooled machine, so maybe in the basement somewhere, right, where you couldn't bring in outside air and cool your electronics. So eventually, the PERCS machine was announced as the IBM Power 775 supercomputer. So we had the charter of writing the software. So we knew that this would be a good platform to write the distributed declustered RAID software for. So many disks, lots of CPU power. But in our heart of hearts, we knew we wanted to get it moved to an off-the-shelf hardware. So we weren't really doing this just for, we were being paid by DARPA to do this for PERCS, but in our heart of hearts, we knew it would be processor independent and OS independent. So we were doing it for AIX and Linux on this computer. But it had a Power 7 or Power 8 processor core. The interesting thing that happened right about at this time, this started in 2007, was that CPUs were now fast enough, right, these 1-2 gigahertz CPUs were now fast enough that you can run a Reed-Solomon erasure code in the CPU at full memory speed. The whole storage industry, like NetApp and all these companies, did RAID erasure codes in accelerator hardware off to the side. And so just like in the grand history of computing, things get moved into the CPU as they go faster and faster and faster as performance doubles used to double every 18 months, not anymore. So that was the last thing that just got crossed. And around 2004 or 5, a single CPU could do read-Solomon erasure code at full memory speed without any special acceleration hardware. And we knew this was true for the power chips. We also knew it was true for Intel. So we had one of the guys in the team had a very clever algorithmic way to implement a Galois field with 4 bits. You'd use 4 registers, 64 registers in parallel, and a very clever way of doing exclusive ORs and implementing the algorithm at full memory speed. So you could do everything in software under an operating system. There were fears that, maybe the operating system would introduce uncertain latency in disk operations, but that hasn't been borne out. So I managed the team, developed the software. Really didn't take a whole lot of management because Jim is such an outstanding architect.
Was the team in place when it started, or did you bring people in?
We brought a couple people in.
Okay, but these were all people at IBM mostly who were there already.
IBM Almaden wasn't exactly growing in size though at the time, so it was kind of painful from that perspective. They had spun out the disk people several years before that to Hitachi. IBM had decided, what happened is they kind of made a slip up. One of the enterprise disks they did, I can add the name later, they outsourced it to a group in Japan, and it quality suffered. And it was the impetus that caused IBM management to get out of the disk drive business. So IBM sold all its disk drive business to Hitachi. Now most of Cottle Road is apartment buildings and a few Hitachi buildings, but and it's all concentrated now in Western Digital. But that was kind of the transition that got them out of disk drives. But so Almaden has said IBM Almaden Research has kind of had to reinvent itself. What other things will we work on besides just disk drives? A lot of people thought that IBM got out of the storage server business too, just because they got rid of the disk drives, but that's not the case, right? IBM still, and to this day, still delivers storage servers. So we built this highly complex, almost 1 million lines of code, distributed RAID software. We announced it on 11/11/11. I'll never forget that date, November 11th, 2011. IBM, we announced the GPFS native RAID, or GNR, for the P775 supercomputer, which was mainly procured by, since it was liquid cooled, perhaps they understood it, meteorological forecasting agencies around the world, the European, Canadian companies, government agencies, obviously, and universities. But, the numbers sold were limited given its cost.
You mean of the supercomputer?
Yeah.
Yeah, well, I imagine that was pretty expensive.
I mean, it worked, it was reliable. Our software worked, it was reliable. One thing to comment about declustered RAID before I go on to to what we did next. The theoretical reliability of the clustered RAID is remarkable. Jim Wiley had done some simulations. If you take some data and you randomly distribute it, you have to remember where you put it. But if you randomly distribute it, and then a disk fails, let's say during the rebuild of that disk, another disk fails. So let's say you have a 2-fault tolerant code. Because the data is distributed across the disks randomly, when a disk fails, the number of what are called stripes, or chunks of unit that need to be restored, is a fraction of all the data. it's like case of distributed across 8 disks. It's like 8 over the number of disks, the fraction of data. So now when the second disk failed, the fraction is that fraction times 7 over the number of remaining disks. So the amount of data that has to be restored decreases geometrically very quickly. And so the probability of a failure during that restore is dramatically less. And so the reliability on paper goes up to pretty quickly to hundreds of thousands to millions of years. In fact, 3-fault tolerant declustered RAID on paper would have an average mean time to data loss greater than the age of the solar system. And we did a lot of papers and simulations and studies, and I hope to do a paper, but it's kind of like the key to long life. Whereas if you take data and just put it in a chunk, you put a chunk here, you put a chunk there, you put a chunk here, you put a chunk here, which is the way RAID normally does it, and you have a failure here and a second failure here, you have to restore all the data in that chunk, which is just that fractional chunk of all the data. And so the reliability of that is not very good compared to declustered RAID. It's just incredibly dramatic. And if you're not careful, you can overhype it. So some IBM salespeople would say, you'll never lose your data with our declustered RAID system, because the mean time to data loss numbers were greater than the age of the universe. Well, that's not quite true, because you have bugs in your software. No software is bug-free, and not so much maybe because it's a bug in the software, but the hardware does some weird thing, right, which causes your software to not recover properly under some conditions. So, even though we inherently declustered RAID has non-intuitively remarkable mean time, reliability, and remarkably large mean time to data losses, or just random mean time to data losses compared to conventional RAID. It was important that customers still realize that if the data was that important, they might want to back it up, because there could be a bug in the software. And the software has been shipping now since 2011. This is 2019, so for 8 years now, and the installed base is quite large. But I'll get into what we did next, but the reliability has turned out to be really, really good now.
Did declustered RAID get traction anywhere else other than this product?
We were the main, we were the source of it in IBM, and I'll talk a little bit about that. It is done now industry-wide. Google does declustered RAID. I'm sure other companies do. I can't say for sure, but
because it sounds like it has a lot of advantages over regular RAID.
It does, because the reliability and the rebuild times are so short. What you might send to different data centers is a smaller amount of data as well to do replication. It's kind of scary though if the metadata, which describes where you randomly placed all the chunks, if that ever gets messed up, you can't reconstruct your data.
Well, is that redundantly backed up, or or it just has to?
It just has to work.
That is scary.
Yeah. So sometimes I jokingly imagine that someday if someone walked into Google and changed a piece of code that lost access to metadata, all the world's data would become scrambled.
Yeah, that could happen.
It's people don't realize how sophisticated the storage algorithms are on places like Google. I mean, I don't know all the details. I'm obviously extrapolating, but it's extremely complex based on the papers they've published. Okay, so now the question is what to do next. We've got this really expensive supercomputer thing, which is impressive, but is very expensive. So Roger Haskin introduced me to a marketing guy at IBM in the HPC group, Matt Drozel. And he had an idea of how we could get to market with cheaper hardware. He knew about what I call a hidden channel in IBM, through which, since we were using off-the-shelf components, we could deliver a complete, this is in my words now, a complete systems product to market, bypassing all of IBM's procedures, processes, and VPs because of this channel. And we said, okay, let's go. And the channel was in the X series group. IBM, had X series, which is Intel-based servers. It had I series, which is its older stuff, and it had the X series, which is the 360 stuff, and the Z series, XIZ, or whatever order you want. And the Intel-based stuff, they had a group there called the Intelligent Clusters Group. So if a customer wanted to buy a cluster, that group would get the components, the CPUs, the storage, the networking, assemble it, and ship it to the customer. So we said, okay, well, here are the systems, and there are the customers. And so we went out and sold it. And our same software, obviously it gets better over time, but the same software.
And there was no objections in other parts of
Well,
IBM
I would be
for
on
that?
phone calls, and people would say, who's the VP in charge of this project? We would say, shh. It was essentially run out of the GPFS group underground, and it depended on support from the X series people. So in early 2013, we introduced it formally as we called it a solution as opposed to a product to make sure we didn't step on IBM internal toes. We called it the Linux GPFS storage server, or GSS. And we sold it in configurations up to 1 petabyte per unit. And it sold well, and it gave us lots of field experience. That increased the volume of GPFS sales. But now you're selling a complete system, hardware and software. So guess what? Your revenue is higher. So now you start seeing battles inside IBM, who gets to take the revenue. But again, it's the idea of selling a system gives you better revenue than just software. People want software for free, right? But if you're selling a system, well, I see there's hardware, okay. So I kind of get it. So in 2012, we introduced that, the GSS. But about a year later, IBM, unbeknownst to us, well, kind of decided to divest themselves of the X series group. And they sold it to Lenovo because their margins maybe perhaps weren't good enough. As the Intel servers were becoming too commoditized. IBM just doesn't like doing commodity stuff. They'd sold the disk drives. Now they had sold the laptop group, the Think laptops to Lenovo. So now they sold the X series servers to Lenovo.
Oh, so that's what confused me, because I know they sold the laptop.
Yes,
but
that
X
happened.
series
That
has
happened
nothing to do with-
earlier.
That's nothing to do with laptop.
Yeah, that happened earlier. This was now the servers that IBM
But they
was
sold that
designing.
to
They sold
Lenovo
that
as
whole
well.
group to Lenovo, and to sweeten the deal, they gave them our software as well, our GNR, GPFS native RAID software, to sweeten the deal. So now we'd just given the software to Lenovo, but now we needed a product. So at that point, Matt helped us introduce a Linux IBM Power-based product, and we called that the Elastic Storage Server, and that was introduced in 2013. Now we had to go through all IBM's processes, procedures, and VPs because it used IBM Power line. And the advantage to going with Power is they have a worldwide distribution of spare components. So field support was already in place. I mean, there were lots of rough edges to that because we had many components. It wasn't just one part number someone could call in on. But we basically had the support, the whole support of the Power group. And we help revenues on their low-end Power servers. We help augment their revenues. And it's sold quite well, and it's still selling to this day. We're up to 4 petabyte systems when I left. Maybe it's higher by now. And we introduced both solid-state disk versions and disk versions. So we had the industry's highest IOPS rates, per server, 30 gigabytes per second. Throughput rates, the fastest IOPS and the lowest latencies. Oak Ridge National Laboratory, we worked closely with the labs on their next generation supercomputers. They announced the Summit supercomputer with a 250 petabyte, 2.5 terabyte per second ESS-based storage system. And Livermore, they're still working on this, announced Sierra with a 150 petabyte, 1.5 terabyte per second ESS-based system.
So what time frame was that?
That's just last year.
Just last year,
Yeah,
okay.
so that's very recent. So they're still working on bringing them up. Very high performance storage systems, all running GPFS native RAID. On the market, it's called IBM Spectrum Scale, by the way. GPFS is kind of the geeky word for it. So it's been selling well, supported by my team in Almaden. Actually, IBM has awards they give if you hit a certain revenue number, 100K per year. I won't say the other numbers, but up to $1 billion per year. And the intermediate one, our team got recognized for that revenue. Our small team of just 5 or 6 people, because we, obviously people assembled the systems and stuff in manufacturing, but we were supporting it in the field. We were supporting customers. It was like a startup inside of. So we weren't just a bunch of researchers on the hill. We actually delivered a complete systems product and supported it. So with the help of the group in Poughkeepsie, the GPFS guys in Poughkeepsie, with their help and their enthusiasm. And a lot of respect because of people like Jim Wiley.
So was that the last major thing you did? You're now retired
yes,
from IBM.
So yes, so in May of last year, with that going well, I retired. And so 41 years in Silicon Valley. That was 17 years at IBM. The group of us who worked on that are retired now. Many of the other guys retired as well at the same time. And we get together every month. The group is called Romeo, Retired Old Men Eating Out.
Great acronym.
It illustrates the incredible humor, wry sense of humor that Jim Wiley has. One thing that happened, just to comment at IBM, in the spring of 2013, ARC decided, just because of an investors conference, they needed more space, and they divested and destroyed their library. They had this large library of 5,000 bound scientific journals, 20,000 books, and they decided to get rid of it just to make room to have a conference.
And the physical library. Yeah.
Physical library books. People just don't look at books much anymore. But we wanted to find homes for many of the journals, so I contacted the Niels Bohr Institute, and they had a worldwide distribution list of libraries, and we were able to distribute about 5,000 bound journals to other libraries. Palo Alto Mathematics Institute took all the bound issues of Physica, physics letters. One thing that was interesting is that I was in the hopper as books were being thrown into the recycle bin, to become intelligent toilet paper, I guess. Out comes this bin of the Proceedings of the Royal Society of London from 1900 onward. These books had been kept in Australia first. And that's like when the atom was discovered, right? And this is, Rutherford and all this stuff is in it. Yeah. And I thought, well, someone might want that. And so I looked at the list we'd sent out, and it wasn't in the list. Library didn't know they had it. It wasn't in the inventory list. So I ended up preserving it, and it wasn't thrown away. So, and a whole bunch of French journals were thrown away, and I just watched that French movie about the French Revolution where they were decapitating the French elites. It was like, oh, we need to save those. So that was kind of disheartening, but we were able to save a lot of the work. Okay, so that was IBM.
So I guess so our next section will be on the Computer History Museum itself.
Yes.
So did you, and you started long before you left IBM, did you find retirement enable you to do a lot more now suddenly at the Computer History Museum, or was it just that you just kept doing what you were doing?
Yeah, it was more I just kept doing what I was doing. I was really grateful, is the right word, for IBM for allowing me to actually start volunteering at the Computer History Museum. I started volunteering there first in 1998, but I'll get into the whole story, but in the year 2003, I basically started coming here every Wednesday. And no one complained. It was a freedom that if I was at a startup, I never could have done that.
Yeah, because you took time off.
We had more normal work hours at IBM. We still worked long hours, but instead of being 24-hour days, they were maybe 10-hour days. And on Wednesdays, I would just work longer, right? If I was here, I would just work into the evening. I don't know if you remember at Xerox, when I was working for you, I used to stay up really late, and I would wait till 11 o'clock to call my girlfriend to reduce the phone bills.
Yes, I remember that.
So I was used to staying up late. That's funny.
Yeah, so that probably helped encourage your work here at the museum.
Yeah, they didn't discourage it.
Because
No one said you can't do that. So, and I was basically helping IBM's presence. You know, IBM doesn't have much of a West Coast presence, and so anyway, so I when I first started visiting the Computers Museum, they had the Quonset huts at Moffett Field in about 1997. It was all in little Quonset huts, and it was kind of a geeky dream. It was like a Valhalla of computers where they go to die, right? And all this stuff was crammed into Quonset huts. And I started acquiring and donating small classical computers. I founded IBM 1130. I founded IBM 604. That was the 2 calculator. I found like an IBM Trust memory unit. So I started donating stuff to the museum. Personally, I have some old classical computers. I have a collection of DEC computers. I have an 18-bit PDP-15 and
Yeah, this is, so I was going to say, you have your little museum,
at home,
computer museum at home as well.
Yeah, an 18-bit PDP-15, a 12-bit PDP-8M. I had a PDP-12 for a while, and I had a HP 2116, and I still have an HP 9100B calculator, the original calculator used during the Apollo missions, you know, kind of.
Yeah. And a number of Xerox.
Oh, and I had a Xerox, Dandelion. I had a Sun 4200. The Dandelions I gave back to Xerox PARC, to Kathy Jarvis, to her legacy lab. But then the next year, the marketing guys wanted the space, and they shipped it all back east, which really disappointed me, because I hoped to use that as a base to show it to people here.
Yeah.
So in 2003, I was part of the PDP-1 very early, just for a few sessions, the PDP-1 restoration team, which had been started by Mike Chaponis. And he asked if anyone, he had noticed, there I interrupted that sentence, he had noticed that there was an IBM 1401 on German eBay. And he said, is anyone here willing to lead a project to restore it? And so I raised my hand and said, I just joined IBM, right, a couple of years before, and I do nothing but IBM computers. So I raised my hand and said, sure, I'll do that. Because when I was younger, I remember I didn't like business, big business. IBM was business, you know, do not fold, spin, mutilate, you know. I was into scientific computers, you know, DEC, who's IBM? I knew nothing about their computers, except maybe a 360. So I said, sure, I'll do that. And then my next question is, what's an IBM 1401? So then I look it up on the web, and I go, holy shit. It's a 5-ton, you know, 12 kilowatt computer from the late 50s. And so I was thinking, what did I get myself into? People told me, they said, well, you know, there's an IBM retirement club in the Bay Area. Why don't you put an ad in the IBM retirement newsletter? So I did that. I wrote a little ad that IBM 1401 needs help. You know, please come help restore one. And the next week, this is in 2003, I guess, or maybe early 2004, about a dozen retired IBMers just show up here. And they'd all worked on 1401s or in manufacturing in San Jose, and they were all interested to see if they could help. And they all volunteered, and many of them stayed with the project to this day. So I had a team. And, you know, we divided it up into IBM 1401 isn't just a single thing. It's like 8 or 9 things that need to be restored. I'll show a picture, but, you know, there's the CPU, there's the extended memory, there's the card reader, there's the printer, then there are 4 tape drives. So, you know, it's like 6 automobiles and a box full of 2,000 printed circuit cards with 10,000 transistors. So, you know, we had a lead on the CPU, we had a lead on the restoration lead on the printer, we had restoration lead on the tape drives, restoration lead on the card reader and punch. And so we started. But one thing we kind of noticed was that every week, well, the German machine came here. IBM helped pay for the shipping, which was really nice. You know, IBM really had their act together. We just said, there's the computer, and here we are, and they did everything. Went to the guy's house. He had stored it in his garage, outdoor garage in Germany for 30 years, his auto garage. They crated it up, put it on a ship, and it arrived in the loading dock here, all paid for by IBM. And after about, we got it put together, we got the team working on it. We continued to find failed cards in the CPU. Like I said, there were over 2,000 cards, SMS cards about this big. I should have brought some. And every week we'd find, Ron Williams would find one or two bad cards. And one of the problems was solid state is supposed to last forever, right? Transistors last forever.
Yeah.
Well, it turns out that when they made germanium point contact diodes, they found that the glass adhered to the leads better if there was iron in the leads. Iron apparently glass adheres to iron. So guess what happens if you have iron leads in German moist summers for 30 years?
Rust.
They rust. So many of our diode leads were rusted right at the junction point, and many of the transistors, they put iron in the T05 cans, would either be rusted right at the leads or rusted on the cap. In fact, you could push sometimes some of the transistors, if they bent over, the leads had rusted through. That was one of our common failure mechanisms. And so I was with 2 cards being discovered every week, I was starting to think, did I just buy 10,000 rusted transistors? Yeah, the cost for the system was about 20,000 euros. That's when I learned you should price in dollars because the euro declined by the time we bought it. I just pay $25,000 for 10,000 rusted transistors. And there's a lot of corrosion in the mechanical parts as well. We were able to borrow components from other pieces here at the museum in storage. Swap is the right word.
That's the only area you could repair things. You couldn't replace it with new parts.
Well, for mechanical, yeah, or sometimes I can get into
transistors.
that. But transistors, we had to have. There was new old stock on the web, so these there was germanium transistors.
There were transistors.
And we had spare cards if we needed to. We could always take them from the spare cards. But there was new old stock. We wanted not to switch to silicon to keep it, authentic. Germanium is a poor transistor technology. It turns out they never really did figure out how they work, to be honest. So we had point contact transistors. I'm sorry. The first transistor was a point contact transistor, done at Bell Labs. The very second type of transistor was an alloy junction transistor. You have a base and you melt on an emitter and melt on a collector and have little wires. That's the kind of transistor used in the IBM 1401. Alloy junction germanium transistor. When Bardeen and Bertan and Shockley was the manager, they discovered by really experimental, not by doing quantum physics, that by putting little points on, they were looking for a solid state transistor. You can read all this in the history books. By putting little contacts on, they were able to get one. But they didn't understand the surface states. They really didn't understand why. And it turns out, and it was always not reliable. And the alloy junction transistors are not reliable. It was a black art to make one. And the problem is germanium doesn't have its surface doesn't naturally oxidize. At first they thought there was no oxidation. Maybe there's a tiny bit. So contaminants get on the surface and they cause these charge pools, which cause the transistors to do weird things. Either have low gain or leakage, or loopy transistors, which were a form of memristors, where the IV curve is supposed to go up and over. But our IV curves on some transistors are loops, so that when the voltage decreases, the current doesn't go down the same line. It remembers where it's been. So all these weird, and Bardeen never figured it out. There were whole conferences on how to get germanium transistors to work, and they never figured them out. I like to say, and so silicon came along, and silicon naturally oxidizes, and then you could even put traces on top and have integrated circuits, right? That's what Fairchild did, and all those guys, Noyce and all that. And so I like to say that if germanium were like silicon, if it oxidized, this place would be called Germany Valley, not Silicon Valley.
Well, very interesting, yeah.
Because germanium is named after Germany.
Never thought of that.
Philadelphia could have been Germany Valley if germanium transistors had stayed back east, with the work being done in early transistors.
I probably would have thought of a different name, though.
Yeah, Germany Valley does this. But, silicon means flint. So this is really a Flint Valley. So Germany Valley, Flint Valley. So anyway, so I'm thinking, gosh, we're finding a couple of failed transistors every week. Are we doomed? So I was starting to get disillusioned by 2007. I was just driving along and got this call on my cell phone from Scott Bellflower, who said his father had an IBM 1401 in the basement of his Connecticut home. I said, what? This man had turned his little tiny home in Darien, Connecticut into a data processing center. He had key punches in the family room, the kids all, pictures in their pajamas with punch cards, and he ran a business out of his home. And he had a 1401 in the basement that he operated from.
So operating 1401.
An operating 1401. He used it from late 1980s through 1995. Actually, late 1970s to 1995. 95. The most trailing edge store program computer we know of. Who were his clients? The internet was around in 1995. They were Westchester County golf courses, bar tabs and golf scores, and he would translate into punch cards and supply. So he had operated in the basement of his house, the 12 kilowatt 5-ton system in the basement of his house, and he had a single to 3-phase power converter. He turned it on, the neighborhood lights would dim. Didn't tell his neighbors why, It was kind of a secret, non-secret. His wife divorced him at some point. He said he didn't know why. I think I knew why. And maintenance became too hard after a while. His friends were maintaining, IBM stopped maintaining it. And so eventually shut it down in 1995. But during that entire time, he had a dehumidifier in there, but not since 1995. So I knew there was a chance the rust wouldn't be as bad. So I flew out there. I walk into his dungeon, there's water on the floor. And I go, oh shit.
Not a good sign.
Oh, there's been a leak in the yard recently. I go, okay. But again, it's below grade, and so there was some rust in the back of the tape drives and stuff. But I said, okay, we'll go for it. So in early 2008, of course, it had to be on a rainy day. We got a moving company.
So he agreed to give it to you, or
well, sell it. And I unfortunately had posted the price of the first one, so he knew how much they asked for. So we purchased it from him. I raised some money, purchased it from him, and
so you now had a new supply of cards.
Well, we had a whole system. So we had, it had to be a rainy day. Then I contracted with a local moving company, what are they called, Craters. And what a job that was. I have a whole movie on it, but they'd got, how to get this 5-ton thing out of the basement. And, winches, and they had to reopen an opening, and it took all day. And they loaded the components on a flatbed. The crane couldn't lift the 2-ton CPU with the arm out. Give you an example of, and the trees were in the way. So it was quite, the local TV station came out and filmed us. We were on the evening news, Discovery in Connecticut, this little salt box home. And the shipping company, McAllister, gave us a heavy discount on shipping it to the museum. It arrived here. We put it in the room. I'll show a picture. And I predicted that we knew the failure rate of the SMS cards we had on the German system, so I predicted there would be 26 failed cards, and there were 25 failed cards. So it was much more reliable. And the amazing part about the story is that the very day in 2008, or the very week, the very day that the Connecticut system arrived, the German system started to work. There are no more failed cards due to rusted transistors. So it was kind of like a sibling rivalry, Yeah. You're not going to outshow me. Honestly, the very week that the Connecticut system arrived, the German system started working.
It probably was a random coincidence of the crossover point there.
Yeah. So, it did take me some work actually to convince the museum staff to get a second system. They thought maybe we were getting a little carried away, but I argued that if we were going to have demos on a constant basis, we needed 2 systems. So if one was down, we could still give a demo.
Oh, so the idea was to actually have 2 systems, not...
Well, I was worried that this might become the main one, but because the German system started to work, I argued it both ways, right? But then with the German system also working, I said, well, hey, we need 2 because,
you have 2, yes.
because that way if one's down, we can rely on the other one.
If you can.
So we had we couldn't officially give demos at that time because the room was more of a lab and not a public space. It didn't have two doors. Sometimes we'd invite our friends in, but it became a public space. We remodeled the room in
13, yeah.
2013? Okay, yeah, I can't remember my notes. And I'll show pictures, but from that point onward, we gave a demo every Wednesday and Sunday, except when the building power was out once, and except for just one exception a couple of months ago. So while one was down, the other one would always be working. So we could have frustrating problems with the card reader, let's say, on the Connecticut machine, or frustrating problems with the card reader. Card reader usually gives us the most problems, the mechanical nature of it. And they go on for weeks or months, but during that time, we could do demos on the other system.
So that demo lab actually has two systems
Yes.
right now.
Yeah, two complete systems. Yeah, why don't I show a picture? So this is a picture of, this won't fit on the camera, but it's wide angle because it needs to be wide angle. So this is the lab before it was remodeled. And on the left is the Connecticut 1401. On the right is the German one. So that's the CPU. That's Ed Thalen acting like Mo there over the top. Ed Thalen's the Garrison Keillor of computing history. He has websites that contain so much information about computing history. And this George Aaron, he was actually on the 1401 design team in the late 1950s in IBM. And it was kind of funny story. Bill Florer, who's not in this picture, was his neighbor, and Bill Florer was a member of my team for many years. These guys would take walks together. Until finally, they realized that his walker partner was on the design team at the 1401. And this is the chain printer, the famous chain printer. That's Frank King. There's better pictures of him, who was the lead on the chain printer. Joe Preston on a tape drive, and that's Ron Williams, who was the CPU lead. And it was Ron's work. We didn't have a card tester, so you found bugs by just, what's not working. and Ron, he had the most volunteer hours of any volunteer at the museum ever, because he came every day. Don Luke, Glenn Leah, and this amazing person here is a better picture on the next slide. Bob Erickson, 92 years old when he passed away. The smartest field engineer I ever met. He had all the coolest jobs at IBM. He worked at Los Alamos during the atomic bomb testing when they had the IBM 701 there, so he knew all the atomic bomb physicists. So I had all these stories of what that was like. And he worked in Washington, D.C. during the decoding of the Japanese transmissions during World War II. So he was there when they decoded the transmission of the Japanese general they shot down on the plane. So he had amazing stories to tell and amazingly brilliant. He restored from memory these unit record equipment, these punch card unit record equipment, 50,000 components each. He restored them from memory. Just an amazing individual. And he could restore watches, even though he was over 90 years old. He could. His picture is featured in our room. So one day I decided I needed to get everyone in white shirts in the old IBM tradition, because they used to do that, right? They used to sing company songs and all that kind of stuff in Endicott. So I got everyone to put on a white shirt. They had a narrow tie. They had to rebuy the narrow ties. But yeah, that's Bill Flora, Joe Preston. And some people aren't with us anymore. Bob Faritich is somebody I knew at Sun, a brilliant man. He'd worked at IBM. And he did he brought up the tape drives. He built a tape drive emulator out of analog circuitry and a PC so that we can actually emulate 6 tape drives. We don't need to have working tape drives. So that way we could debug the tape drive controller, right? So we knew we had a good tape drive, which is broken, right? The tape drive or the controller. So his Tau emulator hardware can emulate tape drives, and we can use that to upload software into the system as well. Ed Thalen, Ron, again, the Garrison Keillor of computing has hundreds of websites on the history of computing. Ron Williams, the 1401, Frank King, a young kid from Berkeley that showed up for a while. There's Bob Erickson, 92 years old when he passed away. There's me, George Aaron, Don Luke, Alan Palmer, tape drive, Ron Crane, amazing analog person for us on our team, and amazing stories. These guys did modeled rocketry at Black Rock Desert in Nevada on the side, so they were building large rockets all the time. Stan Paddock, Bill Newman. So unfortunately, the old timers, many of them, or most of them, have now passed. The only ones still with us are
Still, you got that wonderful opportunity of them helping.
Yeah, are Alan, Frank, and Bill. The others are now passed, including Ron.
Yeah, that's a wonderful picture.
Yeah, so that was that. Now, and then this is what the room looks like now. This is the remodeled room. So the German system's on the left, and the Connecticut system's on the right. And this hand key punch is something that Frank King brought in. It actually is IBM model number 1. It's a hand card key punch, type 001. Dates from the middle 1920s. And people need to touch something, right, when they're in a space. And so people come up and you can put a card in, and you push 2 keys at a time for a letter, because remember, the first punch card didn't have letters. The first punch cards were just digits, 0 to 9, and letters were added as an afterthought. The density of characters is so low on a punch card, how many trees were killed because of all of that. But, the chain printers have been extremely reliable. They leak hydraulic fluid a little bit. 1401s have been very reliable. The biggest problems we've had is in the card reader punch units. The German one down here. So that's that project.
So you said you had demos like twice a week for...
We still do, yeah,
Still do.
Wednesdays and Saturdays.
And you told me that young kids were especially interested in this old technology.
Yeah, they're fascinated.
So can you explain more about why was it that it was
Well,
so fascinating?
I think we just create an authentic experience. It's like a time machine. You walk in there and you lose track of the fact you feel like you're in some time warp. You're
and
back
they
in
understood
time.
what that machine.
Well, it's visceral.
About.
Even young kids, it's visceral because it makes a lot. Kids in particular love to sit on the key punches because they make a big noise and they're commanding. In fact, Andy Bechtolstein's daughter, I once had her in there for 2 or 3 hours at night. She didn't want to leave because she was like printing secret messages because they're holes, right? Kids just love the key punches, and they love the big sounds. The chain printer it looks like a T-Rex dinosaur, and that's a computer, So, and parents, enjoy. I know it sounds cliche, but if you watch the demos, people really enjoy them. It's not just me projecting. I mean, I have, it's just amazing.
Yeah, and it sounds it's more visceral. I mean, sometimes a demo is interesting because you understand intellectually what it's doing.
Especially people from that era.
From that era, certainly.
Yeah.
Others, it's a fun experience.
Yeah.
Maybe the kids, it's more the latter than the former.
Yeah. So the way the demo works is that it's too many people to have everyone key punch unless you come in early. So my recommendation was you choose one person from the audience, and that person key punches. They typically choose a woman because women typically did key punching back then. She goes up there and is afraid, and everyone projects into that person. And then you take the names and people who've come earlier, and then we print them on the printer. So then we print out big block names of people, and we run powers of 2 program, 2, 4, 8, 16, which the chain printer gets louder. We need more demo
So you can
programs.
take what they punched out and show it on the screen.
On the printer, no screens. The printer. We actually print it in big block type. If you need to come to one of our demos.
I don't think I've seen a demo actually, but
Wednesday, 3 o'clock, Saturday at 11.
All right.
Yeah. So then we print it out on the printer.
All right. That's what I mean. It's the computer printer. Yeah.
Yes, the 1403, the chain printer, 100 lines per minute. It makes quite a racket. We gave a system to what's called the TechWorks, or the Science, Technology, Innovation in Binghamton, which is next to Endicott. We gave them I helped get them IBM 1440 system and a 1403 printer. And as a student project, they built an interface between IBM PC and the 1403. It's a Nancy 1, slightly more advanced than ours. And the students characterized the 1403 as a cross between a machine gun and a typewriter. Because, these hammers fire. The page moves, the ribbon is wide, the hammers fire and push the paper against the ribbon against the paper.
And the sound sounds
and
like
the sound sounds
gun.
like machine gun, yeah. And we haven't done the computer music yet, chain printer computer music, because we were afraid to break a chain. We only have one spare chain, but one of the engineers in Endicott, the Binghamton facility, worked on the 1403, and he figured out how to rebuild a chain. So what we thought was impossible, in fact, the machine shop at IBM Almaden wouldn't take it on. He actually built a fixture and was able to build one, which we're currently using. It's this long string of little tiny 2 mil wires, and all the slugs are mounted to it. So it's been fun. So one of the things that the project did is it allowed me to really learn in depth the history of computing, because IBM was very early in it, right?
Yeah.
So I had a chance to, over the years, to talk with Fred Brooks, exchange emails with him, Mythical Man Month and the 360 program. Chuck Branscombe, who ran project manager of the 1401 program, he ran basically all of IBM. He was like the president of IBM for a long time. Learned a lot of history. The predecessor to the IBM 1401 was called the Worldwide Accounting Machine. It was actually started in the early 50s when IBM was losing business to Machines Boole in Europe. And we need a more flexible accounting machine. They set up 3 projects: Poughkeepsie, Paris, and Germany. Paris won. So the Parisians started to build it. And they used a plug board instead of stored program, so it came back to the United States. Maurice Popov, who was 92 and is still alive, he ended up heading up to the IBM Research Lab in De Gaulle, and Lugode, next to Nice later, felt it was kind of their machine, because Fran Underwood, the designer, used all the data paths from his machine, from the Worldwide Accounting Machine, and just added an instruction set to it. But no one, they kind of half thanked him. No one ever really thanked him for what became the world's most popular computer. So when I called him in 1998, he said, "You're the first person at IBM who's talked to me in 35 years. And they'd built him a little scale model, 1401. So anyways, a lot of fascinating history. He's still with us.
So you said you told me that it had won an award.
Yeah. So in 2014, Tony Sale, who had restored a Colossus decoding machine at Bletchley Park. They're housed at Bletchley Park right now, at the National Museum of Computing. They have an annual award for computer conservation, so we won that award in 2014. Recognized achievement in the area of computer conservation and restoration, and that was in London, so that gave me a great chance to meet the British Conservation Society people and go out to Bletchley Park.
So do you think the museum will ever do another project like that?
Just before I go on to the next one, and in May 2017, that same museum, the National Museum of Computing at Bletchley Park, had a conference on restoring computers, and I gave a presentation on wrote a paper and gave a presentation on the 1401 in 2017. Okay. So one last story that was fun on the 1401 is in 2008, we realized that 2009 was going to be the 50th anniversary of the 1401. So we spent all this time getting the system to work, and I was thinking, well, where's the architect? Where's the designer? This was the world's most popular computer in the mid-1960s. 1 out of every 2 computers was a 1401. So where's the dude? And so we knew his name, Fran Underwood. And you would Google it and nothing would show up. That'd be odd, except maybe people wondering, where is he? And I eventually found a hit on a music website where it said, Fran Underwood is my father, and I bought this CD for him, who was the designer of the 1401. And the title of the CD is IBM 1401, a User's Manual. It's a piece of music. And I thought, this is weird. So I know he's still alive. The review was written a year ago. And what's this thing called IBM 1401, a User's Manual? So it turns out that a young avant-garde European composer, Johan Johansson, in around the year 2000, finds this reel-to-reel tape in his father's closet, and it's of the funeral ceremony of their IBM 1401 in Iceland. The 1401, like in many places, was the first computer, a store-broken computer in Iceland, and they liked it so much. They had a funeral ceremony. They recorded on the tape, and on the tape, if you put an AM radio on top of a 1401 or other computers of that era, and you run a program which tries to present musical sounds like a melody, it gets broadcast through electromagnetic radiation, there were no FCC requirements back then, into the radio, and it sounds ethereal and mysterious. And so they had encoded a famous Icelandic classical music composer, and they played that through the 1401, through the AM radio, and it sounded mysterious and weird. So he was so inspired by that, he wrote a symphony to the 1401. So it's the only symphony I know of written by a human, not computer generated, to be performed by humans, right? Not computer synthesized, and dedicated to a computer. And if you go look on YouTube, there's even a modern art dance piece that goes with it. This woman writes on stage. It looks like she swallows a 1401. It's meant to be birth, life, and death. And it was performed as part of Johan Johansson's road shows throughout Europe, probably 100 times. And he did tours of the United States. And I went to one of his shows in San Francisco, and the young kids were in the audience. It's kind of like grunge. You know, he would have movies of old black and white industrial processes, and retro and grunge is kind of cool these days. And I'd say, well, we have one of those, and the kids, because we're so old in the audience, the kids would go, really?
So you can go to YouTube and find.
Yes, it's music? On. Yeah, and the music is on iTunes. I mean, the symphony is out there.
It's called the 1401.
It's
symphony?
Called IBM 1401: A User's Manual.
An
odd name, and he got that name because of a very famous book called Life: A User's Manual by a French author. But it is a conflicting name because and the movements are called 1401, 1402, 1403, and 729. In fact, one day I was driving actually to Hollister, which is where my father grew up, and on National Public Radio, Michael Verman on All Things Considered, he goes, now we're going to talk to the composer of IBM 1401: A User's Manual. And I go, what? I'm driving down the road. This is way too much nostalgia. So there's a 5-minute interview where he's talking about the importance of old computers and preserving them and the beauty of this symphony. And I go, okay, this is off the charts. So, you know, I met him. He came here later. He wanted to extend his movie. He wanted to extend his symphony. He wanted to do a movie based on the 1401. Morrison was going to do it. We were trying to get funding for it. But then, okay, so did you see the movie The Theory of Everything about Stephen Hawking's wife?
Yes, I did. Yeah.
He wrote the music to that movie.
Oh, he
that
did.
Kind of bicycle music. And did you see the movie Arrival? You know, the
Yes.
big... He wrote the music to
Also,
that.
okay.
Very powerful
Johansson
music.
is his name.
Huh? Johan Johansson. So I'm all excited, like, let's go and let's try to find funding. But then he died of a drug overdose last year in London.
How sad.
So anyway, so we have to back up. So I know that Fran Underwood is alive because his daughter bought him this CD.
This is the father, Fran.
The father, yeah, is her father. So I look on people finding websites, and there's this person named Fran Underwood in Texas, and about the right age, I figured. So okay, so I try to find information, and there's nothing about it. I try to contact the house, no answers, just nothing. So I go, okay, I'll try the neighbors. This is where everyone has 2-acre lots in the middle of nowhere, Lockwood, Texas. And I called a neighbor, and I said, they answered, and I said, do you have a neighbor by the name of Fran Underwood? And I hear someone in the background say, don't answer the question, it's a bill collector. I said, no. I'm calling from the museum. We're trying to find this man because he was the architect of the world's most popular computer in the 1960s. And so they said, can you put a sticker on their door to have him call me? And sure enough, 2 weeks later, I get this call from the daughter, and he's on the line listening. And so she called me back. And so I kind of had to befriend him. He wasn't sure why I was interested. And she had worked for IBM, moved to Lockhart, tried to set up a Java cafe, but Lockhart is strictly cowboy country. It didn't do well. They had to rent out their house. And so I went and did an oral history on him in his house. And he has an amazing story, Fran Underwood. He started as a mechanical engineer. He wanted to be a design engineer. If you were hired at IBM as a design engineer back in the early 1950s, you know what they had you do? They had you go to the assembly line and assemble 3 unit record pieces of equipment, 50,000 components each by hand. And then he learned logic design from Claude Shannon's first student, And then he worked with this guy named von Neumann in the Advanced Development Lab at ASDD and at IBM in Endicott. So he really brought himself up, and then he took over the Worldwide Accounting Machine and gave it an instruction set. Amazing
So when you
story.
interviewed him, how old was he?
Oh, he was up there, in the late 80s or mid
Late
80s.
80s,
And
okay.
he had gotten a stroke a few years before, so his voice wasn't as well as he had hoped. And I said, your story is so amazing. We're going to do a 50th anniversary of the 1401, next year in 2009. You have to come. If you come, you'll get a standing ovation. And he said, I can't travel, blah, blah, blah. And so then he said, well, you need to contact Branscombe, Chuck Branscombe, and he was the project manager. So I call him, and he goes, I was waiting for your call. He somehow knew we were restoring a 1401. And then he said, well, you need to get the marketing guy. He's in Saratoga, California. So I found him easy enough, Shel Jacobs. And so I had the three key people who just rocketized this project. It was called Space, actually, at the time, because this was during the era of Sputnik, right? And so everything was about space. It stood for something. And so we worked on a presentation. They gave a presentation. The IBM, John Iwata, director of IBM Communications and Marketing, sponsored it and came. He said, these are like the three NASA astronauts of IBM, because they gave an amazing, it's on YouTube if you want to see it. And people have told me at the museum it was the best evening they've ever experienced in terms of a history event,
that's
not a
amazing.
future-looking event. 500 people showed up, and Fran got a standing ovation.
Just like you promised.
and like people like the guy who was the architect of the Alpha, Dick. One day I was in the 1401 lab, and there's this guy cleaning our floor, and it was. He brought his son in to try to get a summer job, and it was Dick, the architect of the DEC Alpha chip, who I had indirectly competed with his son. And I said, he came to the 1401 event because he loved the 1401. It was he thought it was a cool machine. It's amazing the number of people who I meet who know the 1401. It's just remarkable. But I would never think they would know it. The man who did Smalltalk, what's his name?
Yeah, I'm drawing a blank.
Guess what his most favorite computer is?
What's the 1401?
Because it was his first computer at an Air Force
Yeah,
base.
everyone has nostalgic reasons.
Yeah, Dave Liddell was his first computer. So anyways, it's just amazing.
Well, I think it's an amazing project, and you've given the world a wonderful legacy with this project.
yeah, because it helps really.
Otherwise, it would have been forgotten.
Well, and it just represents that era when computers were kind of human-sized, and they weren't
Even larger, like room-sized.
room-sized, and they were intimidating because people overhyped them, but they're not as. Today they seem to be tracking devices and personal invasion devices, right? There's not even an operating system on a 1401. It wasn't hooked to a network, right? So it was kind of a tame animal. I mean, companies, the face of them were punch cards, which were kind of dehumanizing, but little did people realize what was coming.
Yeah, well, it was just tech stuff.
Yeah. So it's been a lot of fun. And by the way, one of the key aspects about the project is to get younger people involved, because otherwise we can't keep it going. So even though much of my team is now passed, we now have 6 younger people on the team. So they're
Keeping it
in their
maintained,
50s and 60s,
Yeah, that's good.
and including one guy in his 40s. No, 2 people in their 40s or maybe 30s. So, and they're enthusiastic about it. And so you have to kind of find people who are either retired or are willing to come in
Yeah.
from work.
I mean, it's a certain type, but if they wouldn't, yeah.
So it's still. So I think we can keep it going for a long time.
All right, so perhaps in the last segment, if you could reflect on your very busy and long career, what you say you have a number of lessons learned. I don't know if that's what you want to focus on, or
Yeah, it'd be fun. First of all, I guess I'm most proud and grateful to have had a chance to work at some of these firms, right? To be in at least 2 places that were instrumental in changing the direction of the market. The Xerox STAR and the Sun SPARC projects. It actually represented even a transition in computing from kind of sys computing to RISC computing right at that. To have the honor to be able to design your own computer, a computer of your design. You work with people, right? It's not you're not a single person doing it.
But also revolutionary design.
Together with the software and everything else.
Something very different from before.
I was just very grateful for having that opportunity to be on the ground floor of the Ethernet. That was to be able to work with someone like Bob Metcalfe, and at Sun, and be able to work with people like Bill Joy and Andy Bechtolsheim. Amazing. And then, of course, at Xerox PARC, even to get to know people like Chuck Thacker and Butler Lampson. And Alan Kay, by the way, was the name of that person we were trying to think of. We were talking about the 1401. So I just feel really grateful for all that. Since we're talking about people, for some weird chance or luck, the CHM, the Computer History Museum, has fellows, right? And I actually worked directly with five of the IBM fellows. Bob Metcalfe, Chuck Thacker, Lynn Conway, Bill Joy, and Dave Patterson. Directly with them, not just know them. And I interacted with seven others. So I'm really grateful for that opportunity. I would do it all over again. It was just so exciting and so wonderful. So yeah, some of my cheap advice that I learned over the years was, one of the key things I learned, I think this started on the Xerox STAR project, was to truly listen to people. Engineers are not very good at that. Especially in a competitive environment, you feel like you have to have the answer right away. And you have to almost in meetings or when you're talking to people. I told you Bill Joy would talk so fast he would bamboozle people by his speed of talking. But you have to, at some point during the day, you have to sit down, stop, seek people out and listen to them. Because what I found is that typically, especially if you're confused, you don't know exactly what to do next, the answer to the conundrum is actually in the organization. Somebody actually has a reasonable answer, just they're not speaking it, or they're not typing in an email message, and you have to just go sit with the person, talk to them, and give them time, and the answers or directions to go in are there. They don't need to be found outside necessarily, or in a heated meeting where everyone's wasting their time. People tend to clam up in meetings like that. So you just got to sit down and listen to people. The answer is usually lurking there somewhere, waiting to be uncovered. The other key thing is it's better. I have found there's two kind of management styles. One where you don't trust people and you treat them like mushrooms in a closet. I don't think that works at all, but some people have that because it keeps you defensive and rigid, and what am I doing wrong? I better think about it. There's that style. And the other style where you trust people. After all, they went and got degrees, and they're probably pretty good people. They have other stuff going on, but it's important to trust engineers first. Trust them first. So it's better to trust people first, and then ask questions later. It's better to get to the bottom of concerns. If someone has a concern, don't just let it ride. Really find out what it is. And get to the bottom of it, and don't be frightened by what it seems to be a can of worms. If a problem is so complex, don't let that scare you, because it's going to bite you. If you ignore it, it's going to bite you. So you just can't ignore it. You have to. Some of the best managers I know of do that, and they do it better than I do. Typically at these startup companies, you'd have problem surface on a Friday afternoon, when. All you can do is we got to come in on the weekend, guys. But you have to do that. You can't kick the can down the road. So one of my other things I learned is successful organizations. It seems to me it's best if they can have a balance of people that are kind of loony free thinkers and conservative routine personalities. PARC was that way. Sun was that way. So I think it's other companies I know of are that way. So it's really important to do that. It's also important not to hire too many uber egos, because then all they do is they fight. You just get cat fights. So you just one or two at most. And then simplicity is always better. We always say that, but creeping featureism really infects companies because everyone wants to contribute in some way or they feel like they're not being worthwhile. But you just have to resist that. You have to resist, perfection is always an enemy of the good. Sometimes the difference between a successful and unsuccessful endeavor is you don't want to try to boil the ocean all the time. If you try to boil the ocean, it's likely it's not going to work. So, one of the key things that I learned is that my way or criteria for a really good architect, a system architect, is someone who understands their own intellectual limitation. So that if they're really brilliant, they can push the envelope and make a design complex, even more complex, they barely understand it. But a really good architect steps back and doesn't design at he or she's limit. Because that way they can leave room to debug the problem, right? If you make it a little simple for yourself, when it doesn't work, because it's not going to work, there's going to be some case where something fails in a way that can't possibly fail. If you leave some intellectual capacity there, you can then debug the problem. I mean, I've known architects to design something so complex that when thing's misbehaving and getting errors, they just throw up their arms and go, I can't debug it. It's just too complex, because they design it to the limit of their intellectual capability. So you have to step back from it and leave room. And so, like I said, I can count on one hand the number of architects who've known to do that. A version of that was Dave Patterson used to have this maxim, which was projects can only draw from a limited number of cleverness beans. You only get a bowl of a certain number of cleverness beans, and you can't you can't use more. And then an old version of that was the KISS principle: keep it simple, stupid. But I noticed people who tended to say that didn't tend to keep it simple. Chuck Thacker was an example of that. He would say that, but then things weren't that simple. And also an aspect of good architects is they're willing to really do the hard work of not just saying this is the design, go implement it, but attend all the design reviews and all the timing problems and sit and listen to people, really generous and gregarious in their ability to listen to all the problems.
Mm-hmm. It's also seeing the whole thought through to the conclusion rather than just throwing it over the fence. Yes.
Well, they're getting the feedback that way by listening to everyone. Yeah, exactly. If you just throw it over the fence, you're doomed. There's a quote about this in the Systems Bible by James Gall, which is, in dealing with large systems, the striving for perfection is a serious imperfection. One thing that's kind of funny I learned, especially at Sun, is that you kind of had this feeling that if there was a weekend between a problem and a Monday, you could just get it solved over the weekend. But typically what happened is on Monday, the requirements would change. Whatever you did over the weekend became unnecessary. So don't get suckered into thinking that because you have time to work on something, you're doing the right thing. It takes a while to learn that one. A funny one is, it seems to be true though, both that when you're bringing up a new computer, it's so much joy and fun to design a computer, build it, and have it work. I mean, it is such a trip. I mean, because you don't know when you turn it on. Of course, you've simulated and stuff. You made these days. I mean, back then you didn't simulate it, but you don't know if it's going to work. But then, of course, problems set in. And what I noticed, or what seems to be true, is computers act up and falter after midnight. It seems like they always get flaky after midnight. And the other thing is you should never compliment a computer while standing next to it, because it will always screw up right after that. One thing I've learned about software, and a lot of people think that you can eliminate all the bugs in software, but I'm absolutely convinced that's impossible. Software will always have bugs. It's just that the rate of occurrence of the bugs, the interval between bugs, stretches out long enough such that it goes beyond the shelf life of the software package. But
so you don't see it.
So you won't see it because the software package is end of life. So there will just always be bugs in software. And so therefore bugs are always good in the sense you want to find them as soon as possible. So in my restoration work, I kind of came up with a funny inverse of the normal law. In the normal IT world, in the normal computer world, if there's an idea, you have to rush to get it out as soon as possible. If you're late, someone else will beat you. The technology changes so fast, time to market is really critical. Well, in restoring old computers, or preserving old computers, the older it gets, the better it is. So it's the exact inverse of the normal thing, where if you're late, it's defunct. But now the older, so if you're restoring something, it's important not to rush into it. It's important to hold back. There's no harm, because actually a year later it's even more valuable than it was now. So it's really important to move slowly and to realize this inverse law, that the older it gets, the better it becomes. So it's kind of an excuse to postpone doing things. So those are the main. The main thing is, I'm just grateful to have a chance to be here in Silicon Valley when I was.
I think those are valuable remarks for new young engineers who are starting their careers. Anything else you'd want to tell these new engineers before they start?
Well, just always buck the system. Don't try to become a conformist. Right? It's always better to, I think, to be a rabble rouser, and that's one thing that maybe it's a West Coast, cowboy thing. Maybe it's an American thing, but it's always better to, if you can, buck this, because things change so fast. You have to buck the system, because someone else will if you don't. So.
All right. Any other parting shots?
No. Thank you very much, Roy, for doing this with me.
Well, thank you. I mean, I really personally appreciate all your thoughts and the stories, both in this session and the previous session, and many, many generations of people will enjoy them through the recordings.
Maybe.
So thanks again for agreeing to do this.
All righty.